Welcome back to Demystify Sci. Today we have one of the most exciting conversations that we've had in a while, which is with Simon Schack about his Tychosium model of the solar system. So Simon has gone through and he has revitalized Tycho Brahe's model of the solar system, which is not a heliocentric system. It is a binary system where you have the Sun and the Mars as the orbital pairs around which the entire solar system rotates on circular orbits, with Earth sitting at the very center. And this is really wild because at first glance, you would look at this theory and you'd be like, this is absolutely insane. We have had heliocentrism for hundreds of years. There have been tons of experiments done to demonstrate that this is absolutely the case, except for one small feature. Simon has collaborated with a computer programmer from Sweden named Patrick Holmquist, and they have encoded all of the orbital dynamics inside of what they call Tychosium 3D, which takes all of the ephemerides for hundreds of years, thousands of years actually if you calculate it backwards, and shows this model of the solar system is completely in line with all of the observations that we have. And that's kind of incredible because a lot of what we do on the show is we look at scientific theories that take existing data and interpret them through a different lens. And I don't think that we've ever encountered a theory that is quite so radical in its reimagining of what a system looks like.
Yeah, there might not be anything in the entire history of science that has so much data as the position of the planets and stars across so many years. There's just so much data. And I think what you're getting at is the fact that you can take two completely separate models and map them onto the same data with extraordinary precision in many respects for both. I mean, obviously Simon's going to advocate that his model fits better, and in many ways it seems to. But the fact that two completely separate arrangements of these physical bodies in space, in their motions, can give the same observational data is really, really important for what it means to construct a scientific theory and what it means to have certainty in a scientific theory just because it fits the data, right? So something can be extremely accurate, extremely precise, and it still must be wrong because both of these systems can't be happening at the same time. Either the sun is at the center of the solar system or it's not. But the data seems to fit both models, and that's just mind-bending if you think about it. And I think it says something really important when we look to, the science, whatever that means. Whenever someone points at the science, it's like, hold on a second. Hold on just a second. These are all theories. They're all maps for the data. And sometimes they can be wildly conflicting and still extremely precise and accurate. And that makes this a really, really important conversation.
Something that is worth noting before diving into the details of Tychos is that Simon's model is fundamentally geometric. And what that means is that it is taking all of the orbital patterns, all of the celestial observations, and coming up with a geometrical model of how they fit together. But there is a huge assumption about the masses that are involved in this, where Simon suggests that our estimation, our measurements of the mass of the sun and of Mars are not as good and accurate as we think they are. And so that's a pretty big...
But I mean, just to be fair to Simon, he hasn't dealt with it. So he's on one hand saying, well, maybe the masses are correct and we just need to analyze how they can work out. Maybe we need to combine the masses of Mars and Jupiter and all of these things and reconsider some stuff. But he doesn't deal with mass and gravity, and he doesn't take any of the flyby missions to those planets seriously for his own personal reasons, which we get into in the podcast. Because a lot of these flyby missions have recorded the mass of these planets through angular deflection of their trajectories. There's been radar imaging studies of the gravitational anomalies on a lot of these planets. It seems like if you take the NASA data seriously, we have a pretty good idea of the masses of the planets. And therefore, knowing Newton's gravitational equations from just experimentation here on Earth, it's very difficult to reconcile the two. I'm not saying it's impossible, but it is definitely the elephant in the room. So I would ask you to hang on to and put your concerns about that aside and hear the presentation out and see how well this data fits. And then at the end, we discuss the problem of gravity and how that might be able to be reconciled in the future. And so it's something to keep in mind. It is certainly a huge, gaping, open question in this work. But I don't think that even if Simon's model is completely wrong, it still says something really, really profound about the way that we make up models about the universe and how we treat our accuracy and precision as stand-ins for certainty, which I don't think is the proper way to look at science.
And to give a large overarching context for the system and for what we're talking about, because when we start the conversation, we kind of smoothly go into it, assuming that people already have a sense of what the model is. The model is that you have 3 bodies in one system. You have the Sun, you have Mercury, and you have Venus. Mercury and Venus orbit the Sun as the Sun's moons. And then you have Mars, which Saturn and Jupiter orbit. And I don't think Neptune and Pluto are also in there.
I didn't even bring those up.
But they also orbit Mars. Uranus is in there somewhere as well, also around Mars. And so then you have the Sun, Venus, Mercury system orbiting Mars, Saturn, Jupiter, and the outer planet systems, with the Earth at the center on a single small orbit, which takes about 25,000 years to complete, which gives us the precession of the equinoxes.
Really small. So the Earth is just barely moving, essentially. It's like a mile per hour, something like that.
And that's basically what you need to know in order to be able to dive right in. It's a wild theory. I can't even imagine how much work went into putting it together, because Simon has a book that he's written about it that one of our patrons, Zarin, was kind enough to give us. And so this is available online at tychos.space.
It's free. Also, yeah, you can just read it. You can follow along. Also, the simulator is available. The Tychosium 3D simulator. You can go and check that out. Follow along. Probably help you come to grips with what's going on here. And
I don't know that we need more preamble than that. It's a wild theory. It is elegant and strange and perplexing, and just really cool that there's people out there that are working on such fundamental questions that challenge the way that we have constructed a huge body of very difficult to parse knowledge. Like celestial mechanics is hard. That's just the baseline. You have a lot of moving pieces. You have a lot of different cycles that are all overlapping with each other. And so that's what gives you the ability to come up with multiple different rationales for how you take this complex system of cycles and create a unified system.
I think you guys are going to love it or hate it. Either way, it's going to be really exciting. By the way, this project is entirely funded by listeners like you. So if you'd like to see us keep making this show, please consider coming over to patreon.com/demystifysci and giving us just a couple dollars a month, which adds up enormously over time to the point that we can almost afford to put all of our time towards this. And so if you can contribute just a tiny bit, that will go a long way. If you don't want to do that, you could buy a t-shirt down below in YouTube. We have links. If you're listening on Spotify, it should be in the description of the video. We're not making money off those t-shirts, but it'd be really cool to have you rep the Demystify Sci brand around town. Tell your friends about it. Share the podcast with somebody. There's a lot of ways you could rate and review the podcast. There's all sorts of things you could do without spending money too that will really help us reach further and further, which ultimately means that the guests that we reach out to will take us more seriously because guests want to be seen. And so growing this podcast is the single easiest, cheapest thing that you can help us do in order to, amp up the quality of our guests. So with that, please help us out. Consider supporting the podcast and enjoy this conversation. We'll see you next time.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
I think a lot of people are aware of the model for the solar system we have today, but maybe they don't understand the history of how that came about exactly, especially how Kepler took Tycho's data and then how Newton eventually introduced this idea of mass. I think we should maybe set the stage for how the original. So is that what you're thinking, Nastia?
No, what I'm thinking that we need to say at least one sentence, which is that Simon Schack has a model of the solar system that is radically different from the Keplerian model, where the planets have these elliptical orbits, everything is centered on the sun.
It is radically different from the Copernican model, but it's very, very similar to the Tycho Brahe's model, the geo-heliocentric model, which was accepted for 100 years. And people don't know that. People don't know.
Right.
As he died, his closest collaborator, Longomontanus, continued his work for a while and published the big Astronomia Danica, a huge volume, where he gave the Earth a diurnal rotation. So he, which Tycho Brahe hadn't given. So the only thing remaining after Longomontanus died was that our Earth must have an orbit, of course. That's the only logical flaw of their work, which was fantastic. They got it almost perfectly right. I'm sure if they were living now, Longomontanus and Tycho Brahe, they would accept, of course they would say, they would come to the conclusion that Earth must have an orbit too, because every single body in our skies have a local orbit of their own.
And so by orbit, people might think Earth does have an orbit around the sun, but you're talking about
this one, the PVP orbit. This is my own lone addition to Tycho Brahe's model. The PVP orbit, which takes Earth 25,000 years to complete.
Okay, before we get into that though, I do want to. We obviously need to walk through your model.
Sure.
But what the heck happened? So Kepler comes along and bangs on Tycho's castle door and demands access to all this data.
Yeah.
What's the story? Like, why do we have the Keplerian model? Why did people adopt that? What was so revolutionary about it? Can you sort of steelman the mainstream narrative for how we ended up with the solar system model that we have today? And then maybe we can, once we understand that one, then we can talk about the problems with it and what led you to your model.
Michael, this is exactly what I do during my presentations. You see what we're looking here? We're looking at Tycho Brahe, the loser at the time, considered the loser. Well, he's considered a loser today. And Johannes Kepler is considered the winner today. But so that's how I start my presentations. I present these two gentlemen who were always arguing. Kepler just came in and said, yeah, can I help you with something? And I'm going to explain this. The problem was Mars. The number one problem of Tycho Brahe was Mars. He couldn't figure out what it was doing because it is a companion of the sun. So it behaves in a pretty strange manner, compared to the other planets. So he said, Kepler said, I shall figure this out in 8 days. But it took him 8 years before he got to some kind of conclusion, and he got the wrong conclusion. So Kepler, it's a good question. Why was it accepted? Because by fudging and fiddling around with the numbers of his master, he managed to make it kind of work out. But he had to give all the planets. I mean, he only studied Mars. He did not study any other body than Mars. That has to be clear to everybody. He didn't spend any time on the rest, on the Jupiter, on Saturn. He was completely obsessed with Mars. He called it his war on Mars. Well, he figured out a way of making it match, kind of, to make it, there was just like 8 arc seconds, which he had to tune, fine tune. And what he did to make it work, he gave Mars an acceleration and a deceleration. He made Mars speed up and slow down. And then he also gave Mars an elliptical orbit. But there is no elliptical orbits in nature. people have been so completely and been enamored with the elliptical idea of Kepler. And I don't know how to answer your question. Why did they buy that? Why should all the orbits be elliptical? Slightly
And maybe
elliptical.
because the moon seems closer and farther at some points, it was maybe something that seemed
because,
reasonable.
yes,
Yeah.
yes. And that's the important thing to understand. Of course, the orbits are not all centered on each other.
Mm.
They are eccentric, which is different from elliptical. And most people confuse these two words. Elliptical is like an egg-shaped thing. Eccentric is just a ring that is slightly off center from its center. And I don't have a Newtonian answer to why they are all off center, but that comes next. We first must see what best geometry fits observation, and the Tychos does that now. So
well, it's
we
weird
have
because in
working
mathematics,
geometry.
like the eccentricity of an ellipse tells you how squished it is. So that word's kind of been co-opted mathematically, I suppose.
Yes. It's been copied mathematically. It's a mathematical construct which just has been embraced by everyone, and but Kepler was the one who started it all. And
So,
no
so
need for
when
elliptical.
Tychos was working, so Tychos is famed for having compiled. He's this rich dude. He likes to party a lot, but he loves, for some reason, he's obsessed with watching the stars and making incredible catalog of the stars, right? And
Look, Michael, please don't even mention that he partied a lot, and that's just
I got no problem with
that's a
partying.
folkloric lore, which people are, lots of young YouTube guys talk about how funny Tycho Brahe was. He was a drunkard, and he had a little, he gave too much beer to an elk which fell down the stairs. I mean, those are things to discredit the man. He was a very serious man.
Interesting. There's a story in my astronomy textbook about how he like Kepler shows up at his house and he wants to work on astronomy, but Tycho is too busy partying for like 2 weeks and he doesn't have time for Kepler. And yeah, I guess it's part of the myth at this point.
I think that it's
total
unfair
bullshit.
to make
bullshit.
partying a disqualifying factor for figuring stuff out.
What's wrong with partying?
So
we don't
much-
party enough.
Yeah, I
There's
know.
so much
More joy.
No, we don't. For one thing, but it is bullshit. I don't think he was a party crazy party guy. This is something that has built around him because they want Kepler to be, the real serious guy. And Tycho Brahe was he didn't know what he was doing.
But I guess my question is, what was the problem? Like, I mean, you mentioned Mars, so maybe that's it. But why was he unhappy with the Ptolemaic system? Why was Kepler unhappy with it? Is this just about Mars not fitting into that? It just doesn't work.
Mostly Mars. And Ptolemaic system doesn't work at all because they're saying that Mercury came closest to Earth, but it's Venus that comes closest to Earth. So that has to be discarded. So what was in play then was just the Copernican and Tycho's model, and it still is. And for some reason they discarded Tycho Brahe's model because there was a problem, and that's the one I've solved. That's the orbit of Earth, because every single body in the sky has an orbit. Why would Earth? Do you see my mouse here?
Mm-hmm.
You see my mouse?
Yep.
Why would Earth? Look at all these bodies: Mars, Mercury. They all have orbits. Why would Earth have no orbit? Every single body in the sky, everywhere in the universe, has an orbit. So it is a complete lack of imagination to think that we are the only mobile planet. Okay.
Mm. And that's what the original Tychos model was suggesting.
Original Tychos model said it didn't even rotate every 24 hours. So it was all the stars rotating us every 24 hours. And I think we can really discard that idea by now.
That's a lot of motion.
Yeah. That's a lot of very incredible fast motion. And it doesn't, it's so much more logical that Earth is, because we see Mars rotating every 24 hours. And do you know that in my book, I figured out that they say officially Mars rotates on its axis in a little bit more. in 40 minutes more than 24 hours. But that's explained by, I mean, there is a chapter in my book where I explain that actually Mars rotates in 24 hours, 0.0. So Mars is rotating at the same time as Earth is rotating around this for some reason. They are both rotating at the same speed. And you know what I found also quite recently? That after all my calculations and now knowing how the Tychosium works, and we can check it, the Tychosium speaks. The Tychosium gives you numbers now. We discovered with Patrick that Mars is actually moving in space at 107,000 kilometers an hour, the same speed as the sun. So Mars and the sun are two binary companions that move in absolute space at the very same orbital speed.
And your Tychosium predicts the same speed for Halley's comet too, from what I understand.
Yes, exactly. Halley's goes also at the same speed as the sun. Halley's is probably an ejectum. A piece of the sun has been thrown out, and it does 76 turns and comes back to Mama every 76 years.
Okay, well, we'll get to Halley's comet. I want to make sure. So we introduced this Copernican system. Where does Copernicus fit into this timeline of this story, by the way?
Copernicus was predated Tycho Brahe, first of all. I think most people will know that. And he never even published anything. They say that he was afraid of publishing it, so he kept it, under wraps. And there was someone else who published his work. And he didn't do any observations at all, I think.
So Kepler was already interested in this Copernican idea when he went to Tycho.
And you have to wonder why, because Copernicus was very much, everyone doubted the heliocentric model at the time. In the 16th century, while Tycho Brahe was living, Copernicus had really not gained any sort of serious attention. It was Tycho Brahe who ruled at the time. And his system was almost perfect. But what I just tried to say a minute ago, there was one big flaw. Tycho Brahe's system could not explain the precession of the equinoxes. The precession of the equinoxes is fundamental. We've known it for thousands of years. Do you know what it is?
Can you just explain what the precession is for people? I think most people have probably heard of it, but just in case, maybe we can explain it.
Absolutely. I'm going to explain it here in my slideshow. The precession of the equinoxes is that we see, if you look up at a certain star one day, okay, the next year that star will have moved to the left, so eastwards, by 51 arc seconds. Actually 50.3 officially, but I explain in a book where it's a bit longer. It's 51.
Which is very, very little.
Very little. All the stars, the whole firmament just move tick, ticks. It ticks to the left. Understand? It ticks, tick, 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 tick by 51. Every single year. And that means that in 25,000 years, it will have ticked 360 degrees. So what is that motion? Well, that's supposed to be the third motion of Earth in the Copernican system. That should be a wobble. This wobble here, Earth should apparently wobble clockwise very slowly and complete a 360-degree wobble in 26,000 years, approximately. That's the official explanation for the precession of the equinoxes. But it's a very strange wobble because it goes on the opposite direction of its spin and of its supposed revolution around the sun. So it's a very strange wobble. It's supposed to be the sun and the moon that's pushed on its oblate shape, but it is much, I dare say, it is much more intuitively logical to think that we are actually we have an orbit, and that orbit explains ipso facto. It explains the precession. We are moving simply around this orbit, and we are doing this orbit in 25,344 years. There you go. And we are always tilted by 23.5 degrees.
So can we talk about what's the problem with the wobble hypothesis?
Because you say that it's been disproven, but that's a hard thing to track down because, everybody from NASA on down to...
It has been disproven in the most very, very good researchers, very, very eminent researchers, different ones. And they have shown that if there was a wobble that would affect the stars, so the stars do this little ticking, then it would affect also our planets. But it doesn't. We don't see that. Have you
Yeah, I
heard of
tried
Walter?
really hard to track this down because
Have you heard of Walter Cruttenden?
Yeah,
one of
but Walter Cruttenden is also
Yes.
citing somebody else as having demonstrated this. Like, there's no paper that lays this out. There's no data that
I
that
mean,
we could
it's
find
so
that backs this
slow, right?
statement.
I mean, people can, like, I think that we recognize from ancient texts that the pole star seems to be changing, but I'm not sure how good the planets, like the data about the ecliptic shifting is. It doesn't seem like the ecliptic, like, in other words, the plane in which the planets occupy, it doesn't seem like it is shifted, and there doesn't seem to be any record of that, but I could have just missed it too.
You must have missed it. That's absolutely incontestable. I don't know why you're not the first to tell me this, but we have known it for 2,000 years. Hipparchus discovered it 2,000 years ago.
Hipparchus discovered that the planets didn't precess.
That the stars precess.
Oh yeah, that's been
Yeah.
known. We're just talking about the planets.
But the planets, okay, the planets are. I have I think 3 or 4 papers I cite in my book of different people, not only Cruttenden. But they, they have done the work, the research, and they can't see any difference in the positions of the planets, which should be expected if it was us, if it was our axis wobbling. That's it. They haven't found it. It is not observed. So it's game over for their theory of precession. It really is. But what we know is that the planets always come back very regularly. Mars always comes in opposition in very, very predictable ways. Everything is very, very stable, and the stability of the system is one of maybe the strongest point of the Tychos model, because the only thing that all astronomers have missed is this little motion of Earth. We move very slowly, but we do move. I mean, we move by 14,000 kilometers a year. So this very slow little motion has completely confounded everyone, because everything didn't match up by a whisker. You see, they've always been arguing about small inequalities. Jupiter, Saturn would move strangely, or small perturbations, and they've had to, add more and more ideas to explain that. But in the last chapter of my book, I have 41 points where all those things get explained. And even not only qualitatively, but quantitatively. That's why I'm so bloody sure of myself. So we haven't started this recording yet, have we? I just want to tell you guys that I have.
We have.
Oh yeah, we've been recording since the beginning.
We've been recording since the beginning.
You are recording. Okay, all right. So I'm just very, very sure of myself, because it would be such an incredible series of coincidences that I have come up with an idea, okay, with some fantasy, if you like. I postulated that the Earth must be moving, and I wondered, how can I decide how much is it moving? How can I decide the diameter of its orbit? And I came up with this idea, because that we know we are under Polaris, and everyone, all the best astronomers in the world are predicting we'll be under Vega in 12,000 years. So there is this motion going on. But what is doing this motion? They say it's a wobble. I just say it's an orbit. That's all. That's the only difference. And I find my solution much more simple and also credible, because
so
again,
Earth's doing this in your model. Earth is doing this very small orbits. What is tugging Earth in this little orbit? Is that the influence of the geoaxial system, the binary
Yeah.
system?
Yes, that will be answered maybe in a few years' time when we will have, gotten this Tychosium to another degree of explanatory power. I have a very good feeling. I think intuitively, I think that the reason why we are moving around these PVP orbits is actually that our whole system is slowly going around Sirius. Sirius is the binary companion of the sun. So we have different types of binary companions here, of binary systems. We have the small type, which is the Sun and Mars, and Sirius A and Sirius B. They are two small binary systems, and the two of them are double systems, which we have observed so many times in our skies. There are so many examples of a pair of stars revolving around a much further away pair of stars. This we know exists in the universe. So here we go.
But
Our
I might
pair,
add that it's, you spent some time at the beginning of your book prefacing all of this as well. But it is a very, very strange moment when you explain to students that almost all of the other, well, let's say the majority of the other stars seem to have partners. And you're talking about systems having partners also, but it's very strange. And the question always arises, what happened to our partner star? Or were we just a strange star that was born without a partner? It's a really interesting open question, and students are always fascinated by that piece of data.
I mean, lately, in the later years, in the last 4 or 5 years, scientists are finding that all stars are born binaries. You can go to the most important scientific websites, and they will tell you that they are now discovering that our solar system is looking like an outlier, a complete exception. I mean, they are seeing binary stars everywhere, and they are over 90%, all more than 90%. I can assuredly say, because in the 80s, the major expert of binary stars, Heinz Wolf, he concluded that 85% was binary. And we have 40 years since then, we kept discovering binary stars every day. So there must be like 90% that we know of that are binary. So, the remaining 10% is probably, we still think they are single stars because we can't find the companion, because the companions are usually brown dwarfs and red dwarfs, which are notoriously invisible, even to the best telescopes. You know that there is not one single red dwarf or brown dwarf that is visible with the naked eye? Did you know that?
Well,
Discovered it in
technically,
the
our
last
own
few
star is
years.
a red dwarf, I
They
guess.
don't shine with their own light.
Well, I
They
mean,
don't
technically,
shine.
our star is a red dwarf also, right?
What's the problem with people when I tell them, Mars could be a brown dwarf? Oh, no, Mars is not a star, Mars is a planet. Well, Mars is red, reddish orange, just like brown dwarfs are known to be. They don't burn, they don't shine with their own lights, and they're invisible if they are far enough away. So Mars could very well be a brown dwarf. Very well.
Our sun's actually a yellow dwarf.
Is it?
Mhm.
It's not technically a red dwarf?
No, the sun is supposed to become a red dwarf later.
Really? All right, sorry.
There's so many things that we think we know by now because
You
we
should
have
take
these
my job.
fantastic spectrometers and machines to see the spectra of the stars and recognize them. But I challenge that.
I mean, something that I'd really, really like to see is a convincing paper on this problem with the precession of the planets during the equinox, because there's just it's a really difficult computational problem, right? Because there's a lot of different moving parts of the solar system, and over the course of 25,000 years, there's a lot of different dynamics that you would have to take into account to make that proof. And I've heard lots of people cite it, but I have not found a single write-up of said citation. And I think that's just, like, in order to make this super important point, I would like to see that. And that's just for my own selfish preferences.
this is the time when you need to ask yourself, why haven't I found so many papers that tell us this? Well, I would propose that it's being hidden. There's not really much. It's hard to find because they don't want it. They want to have an explanation for the precession equinox of the equinoxes because it's essential to the Copernican theory.
Sure, but
So
I mean, it's like you'd be the perfect candidate to be able to put this proof together because with Patrick, you have the ability
Yeah.
to create these sorts of simulations, and so
Yeah.
you could easily put it, if you constructed a Copernican simulator and then looked to see what the precession was supposed to be like and compared it to the ephemerides, then all of a sudden you'd be able to say if there is precession or not. But I'm like,
we
I
don't
think
need.
that
Anastasia, we
I-
don't need to build that. We
I
know.
think
We
you
know that
do. I
we
think
have
you
tables. We have tables of how Mars, Venus, and Mercury behave over hundreds of years. We have those tables, and we cannot find anything that shows that our axis is wobbling. You see, we already have these things in our hands. I mean, I could never have done this by myself. I'm relying on lots of many astronomers and their incredible efforts to observe the exact positions of all the planets. And I've done some work myself on that, just using the existing data.
Mm.
And okay, I've not, fully completed this verification, but I think it's absolutely. We're gonna find out that it's absolutely there's no wobble, and there's another wobble that James Bradley came up with. It's the nutation of Earth. All right. Have you heard of the nutation of Earth?
Mm-hmm.
The nutation of Earth's axis? Well, that's supposed to be a smaller wobble, which superimposes itself on the bigger wobble. And this is something they found out a few weeks ago. I show exactly what James Bradley's nutation was all about. And it is amazingly just, he saw the celestial pole moving in a kind of elliptical way. All right? He said by 18 by 16 arc seconds, and it's actually 17.6 by 16, and that is exactly the difference between how much. Okay, you see my mouse here.
Mm-hmm.
We are moving every year by a little more than the diameter of Earth. We're moving by 14,000 kilometers, which is 9.5% more than the diameter of Earth itself. 14,036 is 9.5% more than 12,756. Well, that's exactly what Bradley was observing, because since he was looking up, straight up on the northern star, the celestial pole, he himself, it was his frame of reference who gave him the impression that the celestial pole is moving like that in an elliptical motion. And okay, well, I got to show you now. When I'm talking about it, I had to add it to the book very recently. I added it a few weeks ago. Here it is. You still see my screen?
Mm-hmm.
Here you go.
We're still looking at the same Tychos model slide.
Oh.
I think if you've shared a single program, then you'd have to switch
right.
this. You'd have to switch the share onto the other program.
Yeah. Okay. Oh yes. Okay. So here. How about this?
Yep.
Yes.
The Earth's nutation. Okay. Solved by the Tychos. Sorry if I'm just saying it's solved. It's solved by the Tychos. What is this green ellipse here? This green ellipse corresponds exactly to what Bradley saw when he looked up to the celestial pole. It is 9.5% longer than its wide. Well, from May to May, this guy, he was here in May, and he did this, and then he did this, and then he did this. He went around this area with his telescope, and therefore, okay, it's all summarized in this little caption here. James Bradley observed that the celestial pole moved in a slightly flattened ellipse with a major axis about 9.5 percent wider than its minor axis. In the Tychos, an earthly observer will gyrate every year around the trochoidal path. This is trochoid, with a length of 14,036 kilometers and a width of 12,756. All right? These two distances being separated by just about 9.5%. So it's fantastic. This James Bradley was a royal astronomer. All the astronomers have done the work for us already. We don't even have to do it for us. He saw the celestial pole moving in this strange way and gave it a name, mutation. He thought it was another wobble of the Earth. Another one. It wasn't enough with the main wobble that takes 26,000 years to be completed. No, there was another one, a more frequent, periodic. Well, there's no wobble. It's just an optical illusion. Because
before we get too far past this, I want to just put out a call to anybody listening. If you can find us a reference for the shifting location of the planets, because there's tons of data. You can obviously find the stars following the precession of the equinoxes, but I would love to see somebody who's analyzed the ephemeres going back as far as possible that shows that the planets are at different latitudes from year to year. That would be wonderful, and I couldn't find it myself, and I would love it if anybody listening can find that and send it to me.
Mm-hmm.
That would be fantastic.
And
no, it's actually not.
Oh,
sorry.
Go ahead. It's actually
they will not be at different latitudes. There will be, there will be where there will be no wobble on our planets.
Well, if there was precession, there would be wobble, right?
Yes, if there were.
If the planets, according to the Copernican model, the planets should be in different positions. If the Earth is wobbling, then the observers will see them in different locations across.
Michael, the problem is this one. I see what you mean now. That you're wondering about. You're wondering about those guys. I cite in. It's here in which say that the precession has been disproved. They actually looked at also the declination. So it's an angular shift, which we should expect if we're wobbling. It's not about longitude so much. It's about declination. So the declination has not been. I mean, if there is how we were wobbling physically, it will affect everybody around us, right?
Right.
Well, that has been shown not to be the case. So
that's the reference that I would just love to see. I just can't find that in one place. I just would love to have it to point to people when I discuss this model. That would be really nice.
Because that's a piece of data that, if available easily, to just wave the paper in the air, I think is really powerful.
It's got to be out there.
Yeah.
But you see, the problem is only this: the differences will be so slight, and when they're so small, they're always contestable.
Yeah, well, it's like 50 arc seconds a year, or whatever it is. It's very small, but it should be apparent over 500 years.
No, less in declination. You see, less in declination. Longitudinally, it would be. I mean, the 50.3 motion of Earth is no one is discuss there is no argument about that. Everyone sees
with respect to the distant stars.
Yes, the stars are moving by 50.3. That's incontestable. No one is even that you can't deny it. That's the power of empirical observation, man. People, we need to work with that. We can't pretend there aren't hundreds of astronomers who have looked with incredible
that part's well
precision.
established. Yeah, I think it's just the
totally established
ecliptic plane itself,
and it's absolutely regular. And no, wait. In fact, it's not regular, and that's what baffles them as well. The precession is apparently increasing exponentially. It appears to them. So here we go with another graphic I like.
Hey, before we move away from this graphic,
it's okay from this graphic. Yeah.
Yeah, I'm sorry. I had a question.
It's still the same. It's still the same theme. But so you this one, you mean?
Yeah. So can you briefly explain? So you have these two images of Earth that are separated in time by a year, and you have them overlaid with this light opacity yellow ellipse, and then there's the path of the star's apparent position that has this spirograph spiral to it. What is the yellow overlay? What's that lower opacity layer?
It represents the this what we can read in Wikipedia, that Bradley says that he was watching the celestial pole. Okay, let me see where I can find exactly where it says that. Okay, an ellipse of 17.6 by 16 has a 1 to 1.1 to 1 ratio, and this is a 1-to-1 ratio. This
What
is
is it?
1.1 to 1. So he
right, but
he
there's a
was
path of
physically
this.
moving.
There's a path, like there's the path of the star, right, which is the line with the points on it.
Yeah,
And
you
then
see,
there's also this light yellow ellipse that's on top of it, and they don't really seem to overlap exactly. And so I'm trying to understand what the two.
it's from May to May. It's from May to May. This is a 1 year progression of a man standing on Earth, looking up in the sky. He will do this stroke. But you see, this is chapter 22. We need to go to where I explain why this trochoidal path occurs. I call it the man's yearly path. And a man's yearly path is essential to understand. Otherwise, we can't even,
Yeah, I think we have
can't
to
even communicate.
understand the trochoids first. So
We
a trochoid
you
is
need to
basically.
understand that first.
So what is a trochoid? So a trochoid is like
so hard to write this book with you. You need to take one step by step to understand. The trochoid is. It was one of the first things I did when I came up with the speed of Earth, which is 1.6 kilometers an hour, just 1 mile per hour. Okay, the Earth is moving physically in space at 1 mile per hour. From here to here, you see it's from your screen is from the left to the right. We're moving from the left to right. Right? Is that clear? Very slowly, 1.6 kilometers an hour, 1 mile per hour. So a man who starts looking at let's say the North Star in March 21, he will look at the North Star here on March 21, 1 year. Then he will be here on April 21. Then he will be here on May. He will be here in June, here in July, or in August, and he will be up here in December. And then he will come back here. From March to March, he will have done a trochoid. He will physically have done that. And here it is. Here it is, like more pretty graphic, maybe, this one. This is
and
just
so
exactly
the lighter
everyone
overlay
will
is basically it's a silhouette of the Earth that's moving, and so it's basically just a snapshot.
I will probably do an animation of this, a slow animation that shows you 365 rotations of Earth, and they will bring Earth from here to here. But how can I put an animation in a book? I had to do something to show what I was meaning to say.
Sure. I was trying to understand where the ellipse comes from.
You see 1, 2, 3, 4, 5 shapes. Overlays of the Earth, but it's just to symbolize the fact that we are moving from left to right, but we're also rotating.
Yes.
So as we rotate and the sun rotates around us, the sun will be here on March 21. Then we will here in April 21. Then the sun will be here on May 21, and here in June, and here in August, and here in September. The sun will be here, and the sun will be here in December. The other way around, because here it is shown as some guy looking at midnight. So if you're at midnight, you will do this trochoid at midnight. And then there is another one who is showing at noon. This is another variant. This is at noon. This is a guy looking at the sun at noon for 1 year, and that's why he will get this analemma depicted on his photographic plate. Because if he starts in September looking at the sun, he will do all this. He will travel this part of the trochoid, which is 3 times longer than this one, and and they are in the opposite directions. When he starts getting into the trochoid loop, he will go backwards, and that's why the sun seems to go backwards in the analemma, and it's a 3-to-1 ratio, people. So here is a quantitative proof, And it gets even more precise because, you have to read the book to see the numbers. I've been carefully calculating. And this is the first time the analemma has been explained with good sense. I mean, there's no sensible explanation for an analemma in astronomy, in current astronomy. They say the analemma is due to the elliptical shape of the Earth around the sun. Yeah, but that's very, very, very small. That's 0.000167. That couldn't do this huge, fluctuation sideways, fluctuation of the sun. It's 31 minutes. The sun fluctuates by 31.4 minutes in relation to our clocks. That's a lot of time. 31.4 minutes. So that's why our clocks are only right. They are only correct 4 times a year. But so we have worked around this and invented the equation of time, which makes our clock works. But our clocks go around circularly, of course. We can't have clocks that go around elliptically or trochoidally, right? So we have invented the equation of times. And not, when I say we, some really smart guys, some 100 years ago, invented the equation of time, so we could have clocks that gave us more or less noon. But it's almost never precisely noon. Only on 4 dates of the year. You see them here, December 24, by some chance, maybe, Christmas, April 15, June 16, and August 29. And observe these two, April 15 and August 29, lie on a straight line which comes exactly to where the analemma intersects. So there is no lateral motion here of the sun. Well, this is why. Because in August, we are going away from the sun, and in April, the Earth is moving towards the sun. So there will be no lateral oscillation, only in this point. Mm. And look, this little line shows that it perfectly matches these 2 dates. So this is the explanation of the analemma, folks. There is no one that is superior to this. I'm sorry if I sound like boasting sometimes, but I really need to make this clear. I mean, this is 10 years of labor, and I think we've done enough work to show that this is the only valid geometric configuration of our system. Then we can start talking about physics. But in science, I think, my colleagues think that you shouldn't put the cart in front of the horse. You need to first determine one thing, geometry, before start to speculate why this geometry is going on, physics. So physics comes after. You first need, and that's the problem we are in, which we are having now in astronomy. They have put the cart in front of the horse. They have, wished to run ahead and say, yeah, I can explain, gravity. Newton comes and says, yeah, this is why it happens. Well, no, first you have to go back and see what Tycho Brahe was observing and explain that. You can't desume or find come up with solutions to things if you haven't still determined how the things move. You must.
I definitely want to talk about gravity, but I want to make sure that we make it through this model first. And can we just make a quick aside? So you said you've been working on this for 10 years. What got you into this in the first place? Why? Because you weren't coming from being an astronomer since you were a little kid or something, right? You got into this all of a sudden. What dragged you into this?
Yeah, it's not exactly all of a sudden, but yeah, I've never been, taking any university degrees and stuff, and I think that's what actually might have helped me to have an open mind. So that's your question. Many people, ask me this question the first time. What made you start? It just happens to be one of them, at least, the analemma. Because the analemma was something, I was a photographer for many years. I said, why do photographers get this shape of the sun? And you know what? I completely stalled on this thing. I couldn't understand it. So I left it for years on the side. And I said, maybe one day I'll understand it. And it took me, it took me a decade to finally understand it. So it's a fun, my research has been like a loop. I asked a very difficult question, and then went through many others and solved them, I think. And finally, then I could go back to the lemma and explain it. And this is why I really love this lemma thing, because it is verifiable. You can do it every year. Everyone can spend a year taking pictures of the sun. It will do this all the time, and it is totally verifiable. It's something. It's not something, some conjecture up in the air. It is verifiable at any time. And also, we now have, if the big observatories would, this is just dreaming, but if some big observatories would give us some time and verify this with accuracy, I think they will be confirmed. But this is just daydreaming, because it won't happen. Not during my lifetime. I'm very, a rational person. I think no one is going to give me any, accolade for this. It's just not going to happen, because too many things have to collapse before. But I urge people who have open minds or not, invested their lives in this, to look at the Tychos, because it actually solves things that are easy to understand. They're much easier to understand than what they're doing now. They're looking at galaxies and black holes and dark matter, which are absolutely unnecessary things, which I'm also getting there, actually. Maybe my third book will be about this, because I kind of think I understand why they're saying they have a problem. They have the huge problem with dark matter. You know why? Because they're looking at very distant galaxies, and they see planets or things rotating around them at incredible speeds, huge, enormous speeds. That is not, no. They don't match Newtonian theory. So why are they not rotating so fast? Oh, there must be some dark matter that we can't see that speeds them up. No need for that. The stars are much closer, as I say in another chapter in my book, because stars are measured today because they believe that we are going around the sun, right? So I probably need to go back to my slideshow, if you don't mind. And so we should be moving by 300 million kilometers every 6 months. Well, we're not moving by 300 million kilometers every 6 months. We're moving by 7,000 kilometers every 6 months. And let me find now a way. Do you see my slideshow again?
No, we're still looking at the browser.
All right.
So before we move away from this analemma thing, it seems like the mainstream astronomy thinks that doesn't believe the analemma is a problem. Like there's I was just looking at the Wikipedia page for it, and they've got all sorts of numerical simulations and justifications for the analemma based on the tilt of the Earth and its elliptical orbit. Was there one particular thing that stood out to you that was contradictory in that explanation?
In the official explanation of the analemma?
Yeah.
Yes, it doesn't make sense to me. I've read it 100 times, and I don't see what they mean. It is absolutely incomprehensible.
Well,
why would it be not symmetrical? You see, this 8 shape is not symmetrical.
I guess they're saying it's because of the. I mean, it obviously is based on the Copernican idea, but it's based on the non-uniform rate of change of the sun's right ascension, right? So, which is these combined effects of the axial tilt and the orbital eccentricity, which is, mainstay of the Copernican model. Yes. But it seems like they can make it work using that. From everything I can tell, it seems like they can run these simulations using those assumptions and make it work out still.
I've never seen such a demonstration, Michael. That's what you said.
Just check out the Wikipedia page at least. It's
I've been trying to understand the Wikipedia page, of course.
I mean, it's the place to start, anyways. They do a number of calculations here about the different widths and so forth. I mean, they could. I have no idea if they're right or wrong. It seems to have been at least addressed. It doesn't seem like it's a controversy for them, at least.
You see what clinches this for me? What clinches is for me, the analemma, the Tychos analemma. What the clincher is that the quantitative proof I give, because the analemma could be considered as a speedometer of Earth. Because let's explain in the book. It's hard to explain here on radio, folks. I'm sorry. You need to read the book. That's why I wrote the long book, because
get the book, everybody. Get the book. We'll put a link to it down below. You can read it for free too, by the way. It's just online. You don't have to buy it. But we've got a beautiful hard copy of it here, by the way.
Yeah, nice. You really need to read the book. I mean, please don't. While I talk on radio, I know I always forget things that I should say, and so I'm not a big, I'm not a great talker. English is not my first language, and so on.
Yeah, you're killing it.
I do my best.
I think the most beautiful, I think one of the most striking things about the Tychos model, when anybody picks up the book or checks out the simulator, is that it does do such an incredible job of reproducing the mainstream observations, right? So the fact that that there's a mainstream simulation that works for X, Y, or Z, and the Tychos works in a very different way for X, Y, and Z is actually, for me, extremely exciting and bizarre, because look, like, I don't know if you're right or wrong, honestly, about this, and that's not really what I'm trying to do here on this show. I just know that it's incredible that you can fit these two different models to the same data, and they're so wildly different. That's just that says something so profound about what science is, in so much as science isn't always this beautiful, clear-cut solution, certainty thing that we're taught that it is since we're kids. And so if there are two different models that can fit the same system, and I know, of course, you're arguing that yours fits better, fair enough, but even if you just stop at, hey, both these models fit this data, that's freaking crazy. That's not the way that we're taught how science works. And I think that's a really central issue that we have to figure out as a species.
Yes, Michael, and as you say, I mean, it works in spite of the fact I've done away with so many things that are unnecessary. That is, the supposedly variable speeds of the planets that speed up and slow down all the time. Mercury is supposed to speed up by 34% and slow down by 34% in their model. No, look at the Mercury here. Okay, let me just shut off the Mars here. So let's just look at Mercury for a while. Mercury and Venus, okay? I switch off Mars so it doesn't distract us. I switch off the tracing. No, I should not have switched off the orbits. Okay, switch off the tracing. We just look for a while at, this is Mercury, right? Okay, okay. Let's see Mercury. What is Mercury doing in your eyes now? What is it doing? It's circling the sun, right? All the time. It's going around in a circle around the sun. It's not doing something strange. But once you put the trace on Mercury, it's going to do exactly what it does. It will have retrograde periods. So we put the tracer on just Mercury now. And we look at what happens. Let's look at what happens with Mercury. So here you go. This is what Mercury does. As seen from Earth.
So
we will see Mercury going backwards.
Appearing.
But it's nothing magical. It's geometry. This is what will be seen. I switch off the trace now. It still goes around in a circle. So
and this trochoid appearance has been known for a long time, right? This is what led people to the Ptolemaic epicycles in the first place.
Because it works.
Because the basic way that you make a trochoid is you basically stick a pencil or something on a circle and roll it down a line or something, or you can roll it down another circle, and
Yeah.
you get this pattern that
Now we're looking
falls
at
out.
Venus. We're looking at Venus, which is also going around in a circle all the time, but it will go backwards for a period of time. So that's the retrogrades explained very simply. This is just nature. This is nature for you, nothing strange at all. Whereas, what do they tell you? That we are going around the sun, and when we overtake Mars and Venus and Mercury, when there is an overtaking maneuver, then we will see this effect, which is just an illusion. Well, it's not an illusion. It's actually something real. And it is hard to wrap your head around this for the first time you see it, but you can't deny it. It's there. The retrograde motions. The retrograde motions have been such a mystery for millennia, right? Because people really do, and then, if you look at even Jupiter, it looks even stranger. No, let's put it looks strange, yes, but it's because most probably the sun is a big central magnet, if you will, which is connected with all the other planets, just like Tycho Brahe was saying. And so we now put the tracing on Jupiter. All right, let's see what Jupiter does. Now we put lines instead of dots. This is what Jupiter does. It seemingly goes backwards, but we can go a bit faster now. So all the planets have this trochoidal motion, and including an observer on Earth. Now we go close to Earth here. Okay, here is the Earth. We're going very fast now. Let's go very slowly. Let's go like now 1 hour at a time. Okay. We are going from left to right. You understand this? This is the Earth moving slowly from left to right. Well, you will only understand if I show Earth moving like by 1,000 years at a time. So let's do it. I put here 1 second equals 1,000 years, and I just do step forward. Okay. Oh, now I have traces on, so it will be crashing. But we are going around this PVP orbit in 25,000 years. Okay.
This is the precession orbit.
Let's try it again. Yeah, let's try it again. I had it with a trace on, which is not advisable.
So while you're working on that, maybe I can just sketch this out.
Here
for
we
people.
go. Here we go. This is the only thing I wanted to show you, Michael. I click 25 times 1,000 years, and we go around this PVP orbit. 25,344 years, and we'll be back on the same place. We'll be back under Polaris after 25,344 years, and we will be under Vega, which is about here, above Earth, of course. Vega is about here, and in about 11,000 years, we'll be under Vega. That's it. So that's why I call it the PVP orbit.
So maybe can we just zoom out a little bit, and because I don't think that we've told people exactly what the orbital system is that you're proposing yet. So obviously this doesn't look like the nice heliocentric orbit that people are used to. You're proposing actually that there's two main orbital systems. The Earth is kind of stuck between the two. Can you outline, just give us a 30,000 foot view of the Tychos planetary model?
Give you an outline about what exactly do you mean now?
Oh, I just want to set up so you have the sun and you have the Mars, right? So you have you call it a binary system, right? So I want to make sure we haven't actually explicitly told people yet what the binary system consists of. So maybe we can just give them that quick overview before we continue with this.
Yeah, I mean the basics of the system is that Mars is a companion of the Sun, because it's the only one of our inner solar systems planets that actually comes on either side of the Earth. So, like in 16 years time, it will be on the other side of Earth. So this is what Tycho Brahe defines. He came to this conclusion that Mars is doing this. And you know what was amazing to discover many years after I started this research? I suddenly realized that Mars is passing regularly in the middle of my PVP orbit. I mean, I've defined the PVP orbit, the diameter, for reasons explained in the book, but Mars keeps passing exactly in the middle. Isn't that fascinating? So, ergo, the end result of this is now I have to switch. Now why does Zoom work like this? I have to change my screen share.
We see the browser.
You see the browser now.
Mm-hmm.
So
you can share your entire screen, or you can share programs in it. And so if you share your entire screen, as you shift between programs, it'll just shift with you.
Okay, let's see. Entire screen. This you see now.
Yeah, we see your basically the desktop with all the slides.
Okay, so what I'm looking for is this slide, which is what we're talking about Mars being. My goodness, where is it now? It should be here.
So, like, I'm still just going to overview this for people who are trying to hang on for dear life. So, the basic idea is instead of all these planets going around the sun, some of these planets go around the sun, and some of them go around Mars, and the sun and Mars go around each other. And so you have a bit more complexity introduced to the system. But the fundamental difference is that there's two focal points, which are the sun and Mars. Just make that perfectly clear for everybody at home.
Yes, that was pretty well summed up. Yeah.
And so, yeah, we'll unpack that a bit in a minute, because I'm sure people have questions about that, but we'll get to it.
But I mean, I showed this in England the other week. Didn't I show that with Mars? I must have it here. Oh yes, here it is. Sorry. Okay. Of course, here it is. Slide 33. So let's go to slide 33. Okay, here we go. There. Now, okay. Okay, what are we looking at now, Michael and Anastasia? What are we looking at now? We are looking at 4 screenshots from the Tychos, which we were looking at before from the simulator, just superimposed on each other. They are separated by 6,336 years, which is 1/4 of 25,344, right? So 1, 2, 3, 4. Mars keeps passing in the middle of our orbit. This is the Earth going around once in 25,000 years. And what do you know? Mars always comes here in the middle. So it's like the orbit of Mars pivots around the middle where there is nothing. This green dot, is it green for you? This dot here? Well, this one?
Mm-hmm.
This green dot. I call this green dot the secular barycenter of the whole system. And Mars is the one that visits it. It visits it all the time. Every time it comes closest to Earth, which is 56.6 million kilometers, exactly half of the diameter of the PVP orbit, which I came to with completely different, ideas. So this incredible confirmation jumped at me only like 4 or 5 years after I had decided the PVP orbit. Can you imagine? I just realized that Mars was always passing here many, many years later. It was like a gift from the stars. So,
how often does Earth... So, go ahead.
I was just going to say, so what this means to you is that Earth is essentially being juggled between these two binary axes, right? It's being tugged on by these two axes. That's what you mean by the secular barycenter.
Yes, everything you see here is rotating slowly clockwise, as seen from above the North Pole. Okay, everything is rotating clockwise, and it's probably the motion we are doing slowly as we go around Sirius, which is much further away. Sirius is our double companion, the whole system of Sirius. And we must look, if you please, we must look at how much Sirius resembles our own system.
So
if
how
you
often would
read
you
the book, you must
expect?
know what I'm talking about.
Yeah. How often would you expect Mars to come dangerously close to Earth in this?
Nothing is dangerous, Anastasia. Everything is very,
Like, not
very,
even
very.
danger, if it would like just close enough. Because I mean, the way that these orbits are drawn, the
Yes.
orbit of Mars intersects the orbit of Earth, and so presumably at some point they would come very, very close to each other.
No. They are always stable. You need to understand this by using the Tychosium. They will never come dangerously close. They always have the exact same. So Mars will come 56.6 as closest, and it will come like 400,000 million kilometers when it's as farthest, but it will never come dangerously close to Earth. It's a clockwork.
Presumably because the sun is yanking
It's
it
a
out of the
Swiss
way.
clock.
Yeah.
It's a quiz, and nothing crashes in the Swiss clock. It goes on and on and on. Swiss clocks are made like this. All right. So there's nothing. People think, oh, well, now it's going to change. No, it is a perfect mechanism. And there's nothing chaotic about it. And I've done away with so many assumptions they have to come up with. The inequality of Jupiter and Saturn because they wouldn't exactly come back as they predicted. All kinds of small variations in the moon. I mean, the moon is apparently, the motions of the moon are officially not solved. They're not. They're just adding more and more and more ideas to it.
Like what? Which motions?
The motions of the moon are too complex for modern science even to understand. You need to read
You're talking about like the
chapter
precessions of the precession, like
they're adding in more and more terms to it. They're already adding thousands of terms every year because they are missing the fact that the moon is also moving with us at 1 mile per hour. So they will always have these small changes over 10 years, 100 years, which they can't explain because they don't know about the motion we have 1 mile per hour motion. So, and that is also, I mean, I dedicated 2 chapters to the moon, chapter 13 and 14, because I needed a lot of space for that. And I tell you, I've even shown one of the most beautiful thing I think I found with the moon is the exeligmos. Do you know what the exeligmos is? I don't think so. Very few people will have heard of this strange word, right? Well, the exeligmos is a very, very simple thing. Okay, here it is. The exeligmos, Michael and Anastasia, is a 54.1 years cycle, which no one knows why, but after 54.1 years, the moon will return having a solar eclipse exactly over the same spot of Earth. Although Earth will have tilted by 1/12. Okay, so it's 54.1, so it's 54 years plus 1 month. But no one knows why this occurs. There's no, causality given for the existence of the exeligmos. The exeligmos is 3 times, it's 3 Saros. The Saros cycles, maybe people have heard of it, but it's just exactly 3 times 3 Saros. Well, you know what an exeligmos is? The exeligmos in the Tychos is explained like this. It is the time needed for the diameter of the moon to move once from here to here. Imagine a compact disc. This is a diameter of the moon. You see my mouse?
Mm-hmm.
Okay. You want this compact disc to move from one side to another. Well, you will have to wait, in this case, 54.1 years. And you know what? In 54.1 years, moving at 1 mile per hour or 1.6 kilometers an hour, we will cover exactly the known diameter of the moon's orbit. This distance is covered at the speed that I'm saying. I've come forth with the idea that we move at 1.6 kilometers an hour, and look how it matches with the exalicmos perfectly. So it all makes sense, because this is why it will come back to zero. The orientation of the moon in relation to the sun will come back to an exact same point above Earth in an exalicmos. Why? Because we are moving at 1 mile per hour. Stop. It is explained. And here is explained quantitatively, mathematically. Quantitatively means, with the numbers. If we were going at 2.3 kilometers an hour, it wouldn't work, right? We are moving at 1.6 because that's why the number I've come to. If we were moving in any other speed, it wouldn't work. I couldn't have shown this. You see? So, and the book is full of such things. And so there really is a lot to talk about anyway here. I don't need anything. I just wish that people would, put aside some time at least to discuss this, because the amount of things I've just shown, I've just pulled up from this very, very, very slow and careful research are piling up. There's so many now that a discussion deserves to start.
Well, yeah, I mean, the book does a fantastic job of pointing out all of these dilemmas in contemporary astronomy that the Tychos model can explain. I think people are going to balk at some of the physics behind it. Pardon the interruption. I really need to ask a favor of you. Please come over to patreon.com/demystifysci and consider supporting this podcast. We don't have any ads. We're not selling any pills or any junk to you. We're just asking you to support the podcast so that the people who care about it are the people that are paying for it to happen. That's really, really meaningful to us. Plus, you get to come hang out with us once a week for our patron Zoom call. And I'd love to meet you and hear your ideas about what we could do better. So come on over, patreon.com/demystifysci, and I'll see you there. Obviously, the main thing everybody's going to raise their hand and ask in this presentation. And look, folks, go read the book, play with the simulator. It's really, really compelling how well it fits the data. I think that is just mind-bending, first of all. However, most people are going to say, wait a second. You're telling me that the sun which everyone believes to be this huge thing, right? And Mars, which everybody believes to be this rather small thing, are both the focal points of the orbit of all the other planets. And that doesn't make any sense to me, because I know the sun is huge and I know Mars is tiny. And how in the world is this possible, right?
You know that. You know that. You know that the sun is very big and Mars is very small. Okay, fine, good. I agree.
Yeah, so okay.
I agree. And you know what I found very early on in my studies? That Sirius A, our biggest star in the sky, has a companion which is 205 times smaller. 205 times smaller.
Well, less bright, right?
Huh?
It's 205 times less bright.
No, it's 205 times smaller in diameter.
Well, you can't resolve the angular diameter of a star.
They have done that. You go to Wikipedia, they will tell you that these are the actual diameters. The diameter of Sirius B is slightly smaller than Earth. It's 11,862 kilometers. Diameter of Sirius B is 205 times bigger than that. And what do you know? The diameter of Mars is 205 times smaller than the sun. So here we have already something interesting, don't we? We have the biggest star in our sky by far. Sirius is twice as big as the second biggest star. So it's very important, Sirius. First of all, we need to study Sirius more. I mean, Sirius was worshipped by all the big, the Egyptians, and they knew that Sirius was important. So we can't deny that. But they only discovered Sirius B in 1875. Because with the telescopes. So suddenly they found a hugely small, incredibly small little planet, smaller than Earth. being the companion of this huge star, which is supposedly 1.7 times bigger than the sun. Okay? Sirius B is supposed to be 1.7 is times larger than the sun, and Sirius B is therefore 1.7 times larger than Mars. So we have this incredible
there
thing.
is a
already.
well-known feature of astronomy, however, which is that the actual diameters of the stars cannot be resolved visually.
No. They, for very, very distant stars cannot be resolved, but Sirius is the fifth closest star we have, and they have very well determined its diameter, their diameters. They are determined, guys.
I mean, I think they're determined by density calculations based on what they assume to be the mass from the orbits.
No. They determine telescopically. They
can't. They can't do that. Like, this is a well-known feature of astronomy. These are all calculated.
Yeah, I mean, folks can go read it. I mean, we obviously have it. It doesn't matter. Like, folks can go read about it. But I'm pretty sure that you can't determine the angular diameter of a star. But it doesn't matter. The
proportion. No, okay. I agree with you. They can't determine it because they are so wrong about the distance of the stars. Okay, so I agree with it. Now, what I'm talking about, the proportional difference between two dots, which are absolutely for sure, they are united in a binary system, Sirius A and Sirius B, and you're not going to tell me that they are not binary. I mean, that is established. So these two binary bodies are at a proportion of 205 to 1. That is incontestable. That is known. That is absolutely established. Ask anyone you'd like, and there's no discussion about that. And we know, I think we know that the sun is 205 times larger than Mars. But no one has even been discussing this topic before. I had to come and just point this out. I mean, I didn't discover this. I don't have a telescope that's powerful. I just read it in the books. So here we have the first time someone points this out. And what I found more? That Sirius C is supposed to exist, and that has never been observed because it's a French study says it must exist because of spectrographic studies we've done. So if Sirius C exists, you see my mouse here? Sirius C has been very much debated. They don't agree. There's no consensus if it exists or not. But a huge French study concludes that, yeah, it probably does exist. And if it does exist, it's closest to the big one, Sirius A, and therefore it is blinded by the glare of the big star. Now, if we then, and what I'm showing you here to the left, it's not my graphic, it's from an astronomy book. And it shows Sirius B here, Sirius C here, and Sirius A here. So Sirius A has a smaller orbit, just like the sun has a smaller orbit. Sirius B has a larger orbit, just like Mars has a larger orbit. The proportion of the when Sirius B comes closest to the middle is 1 to 7, exactly like Mars, 1 to 7. So we can very well, very reasonably think that the Sirius system is the twin system of our system. It is extremely probable, knowing what we know today. No one has been discussing this. I know this is my idea, but try to at least discuss it, because we have incredible data which makes this very much probable. It is very probable that they are that similar, you know.
I guess so the main difference being that they would tell you that one of the Siriuses is this ultra dense white dwarf, right? That has so much matter, hundreds of thousands of times
and there
the amount of atoms packed into an inch.
Michael, this is why I made this slide, and I showed you my presentations.
Times.
So how did astrophysicists eventually justify the shocking discovery of the tiny Sirius B, which he called the pup because it's so small? Here's how. On Sirius B, the force of gravity is 400,000 times stronger than on Earth. Yeah, but how did they determine that? Did they ever take Sirius B and put it on a bathroom scale to see if it weighed 400,000 times? I mean, that the atoms are packed 400,000 times tighter on that little planet or star? No, they are just assuming this.
They assume it from the orbits, right? So it all points back to
scandalous physical assumption ever. This is
Well,
a scandalous assumption.
it points
So
back to Newton's gravitational equation, right? This is
yes,
how.
yes, because
So
they need to make it work, Michael. This is an ad hoc. It's a confirmation bias, absolutely unscientific way of explaining why they found Sirius B. When they found Sirius B, you can read in all books. It was panic in astronomy community. They didn't know how to deal with it. Eddington said, "No, don't talk nonsense, Sirius B. You can't exist." You know, so it was total panic when they found Sirius B. People have forgotten this, but if you go back and read in the books, you can see that they were absolutely, it was chaos in astronomy. So, but then they came with this incredible, fantastic idea that is super dense. It's a white dwarf, which for some reason is packed, the atoms are packed 400,000 times stronger. But we've never seen that in nature. And mind you, didn't Newton tell us that, wasn't Newton famous for telling us that physics works the same everywhere, the whole universe? Well, this is completely contradicts that. Newton was telling us that no, everything works the same. We have gravity and works the same down there. It works the same down there, here, down there. No, evidently it does not. If Sirius B is such an incredibly exceptional body, so this is ridiculous. What they're trying how they're trying to explain the existence of Sirius B.
I think they're coming at it from the idea that gravity should be the same, and if gravity is the only thing prescribing these orbits, then that little Sirius has to be enormous.
Yes, Michael, that's exactly what I'm trying to tell you. They are assuming that because they need to protect the idea that Newton gave us. And
well, the funny thing about Newton's idea, the funny thing is though,
confirmation bias.
Well, Newton's idea seems to work out pretty good, at least with, like, on Earth, you can just do some basic gravitational experiments.
Nothing to do. It has nothing. Here, okay, here we go at this crossroads. It has nothing to do with how. I mean, gravity. Yes, we know there is gravity on Earth. We know we will pull down. That is one thing. Another thing is how gravity works in space with planets. People are so, they've heard all their life that they've heard all their life that gravity works the same everywhere, right? But as I just told you, it's evidently not the case for Sirius B. So and the whole thing
or
collapses.
We just don't understand. I mean,
the whole thing collapses.
My friend Pierre has a really interesting theory about these dwarf stars, which probably is beyond the scope of this conversation. But let's just stick to our solar system. So, in our solar system, it seems like we have measured this Newtonian relationship ad nauseum, right? We've actually even been to Mars. We've been to Jupiter.
No.
Okay.
Well, you may believe that, but many people understand that NASA is not going to space. But let's not go there. Really, it really is.
Well,
outside of.
Can you deal with?
It's outside the scope of this. But really, it's. This is.
Well, I don't think that it's fair to put it outside the scope of this because look, if the argument is based on the idea that every single piece of data that we've ever collected in space is false, then that's a harder.
Like, can we talk about this without assuming that we've never been to space?
Yeah, Anastasia, let me answer, Anastasia. I've been working on. I've been not discarding anything. On the contrary, I've been using all the data we have been collecting from Earth, which is highly believable, highly reliable. It's written in tables which have been verified 100 times over by different peer reviews. That is what I've been working with. I'm not working with the imagery from NASA, which is a Hollywood department.
But there's a lot of countries that have gone to space. You have the Chinese on the dark side of the moon. You have India. You have Saudi Arabia.
It's a big scam. It's the biggest scam.
I mean, I know people that like my brother when he was in college. They designed a satellite and they launched it.
So here we go.
Well, I mean, I'm just saying, like,
we believe in that because we are in the era of television.
Well, no, hold on. I know someone who designed a satellite in a group of college kids and launched the satellite to space.
Yes, and I happen to live by the European Space Agencies that just down the road from my house, and I happen to know many people who work there, and I happen to know many things about them. this is a discussion for another podcast.
Well,
I
not
know
really.
that they are all very well paid guys. They do nothing from morning to night.
But this is a
They
group
play
of college
cards. They
students.
play games.
This is a
They are
group of
very
college
well paid,
students.
and it's a scam.
They did
It's
it
a
for
huge
free.
scam.
Like
Well, no, this is interesting. This is interesting. I want to hear you out. I mean, hold on 1 second. All right, look. Big lies have been perpetrated in the past. Like, I am open-minded enough that I am willing to consider that we've never been to space. But what I want to ask you is, can you assume that we have been to space and make sense of the data that we have? In other words, we have satellites orbiting the sun. We have orbited Jupiter in one narrative. These things have happened. And there's a tremendous amount of data from these expeditions that seems to confirm the value of the masses of these planets. And I'm curious can we address that, or do we have to?
You mean that this? I mean, so let's see one of these satellites they say they're using. Shall we look at it? I have it on my slides. It's called the Gaia. No, it's called the Parker satellites from NASA. Let us look at it. Here it is. This is directly from the NASA official website. You see this little chicken box here with the tin foil on it? This is supposed to be the Hipparchus satellites, who for years has been circling in a highly eccentric orbit of the Earth and captured and collected highly precision measurements of the parallaxes of the stars with this box here. If you are able to look at this picture, which is directly from a NASA website, and believe that this machine is going at 28,000 kilometers an hour and is capable of measuring parallax, which is something which you need to be on Earth to see. Because parallax is by definition something you need to be on one point and then another point on Earth. How could a satellite do that job for you? It's fairy tales. It's Santa Claus.
I don't understand why.
Hipparchus. Now they have a Gaia satellite, which is you have even more precise 0.00001 error margin of stellar parallaxes. They are completely fooling with us. They are fooling with everyone, and so are the Chinese, the Indians, and the Israeli companies that have just jumped on a bandwagon, which is $1 billion bandwagon, to make us believe that they go into space and land on asteroids. You know, they supposedly landed on an asteroid some years ago, the Eros, and collected some dust and came back to Earth. It is a fable. But this is my opinion.
So
and
do you
that's
think
why I
that
don't want
satellites period exist?
Sorry?
Like, do you think that there's GPS satellites?
No, there are no satellites because we have
What about the
ground-based.
things that you can see in the sky when like the Starlink
Yes.
trains come by?
Yes, they have whatever I would be looking at what is supposed to be the ISS. It keeps passing, whenever over Rome, and it's just a dot. It's a point of light.
Have you ever seen the Starlink trains?
Yes. Well, no, I haven't seen it personally, but I know they exist. So now whatever they have, it's just.
What do you think those things are, though?
Could be laser technology, could be whatever. Do you see what they do with the Japanese concerts nowadays? They have things floating in the air. They look perfectly like UFOs.
TikToks.
So
wait, hold on 1 second.
Okay.
I want to play with this idea that everybody's lying to us about space, but I want to just make sure that we can't deal with it assuming that they're not lying about space. Like, can we assume that they're not lying and still make sense of the Tychos model, or do we have to assume that they're lying about space exploration?
You don't need to assume anything. You only need to,
can I take this data, the Grace satellites? Can I take the Magellan and Venus Pioneer orbiter? Can I take those mass estimates and reconcile them with the Tychos model?
The Tychos does not mention any of the mass things, of the mass paradigms of how to calculate the mass, because this has to come in the second stage of revision of what we know about physics, because now we first have to make sense of the geometry, the correct one, and the only correct one, I boldly say that the only correct one is the Tychos. So then everything has to be postponed. The thing is, when you make a new discovery in science, and it kind of contradicts what has been established, you have to go back to the drawing board, right? And that's what I'm saying. We have to go back to the drawing board for sure.
But we
Because
have all this data, right? We have all this
need to.
data we measure the mass of the planets in lots of different ways, right? And one of the ways you measure it is by the deflection angle of the incoming orbiters.
Michael, we measure them, but we don't verify them. We can't verify. We say, yes, we are sure that Sirius B weighs 400,000 times. Every atom on Sirius B weighs 400,000 times more than on Earth. That's what we are saying. It's an assumption. We are not measuring anything. We are assuming with calculations.
But we actually do go to
years old.
But I'm saying
400 years old.
I understand. Like I like the white dwarf conversation too, but I want to just keep it to like our solar system for the moment. Like let's assume that we've been to Venus, like we've been to Jupiter, the Pioneer, Voyager, Galileo, Cassini missions. They did these Hold on 1 second. We did these flybys, right? And they measure the mass through these gravity assist maneuvers. They also do this Doppler measurements of the particular gravity anomalies on these planets. And they have these, and they agree perfectly with the Newtonian solar system and the Newtonian gravitational equation. And so what I would love to see, and I don't think that you're incapable of doing this, I think you can do it, is to come up with a model for how the masses that have been established could be congruent with this binary system.
Because if that's possible, then it's
complete lights out if you do that.
That's yes, I mean, I would be happy if we could reconcile the whole thing with the old established data. Of course, that would be nice. I mean, I'm doing my utmost to respect lots of old established data, but that's the data I was telling you about before, empirically verifiable observations written down on very, very, very precise tables as viewed from Earth. Okay. When NASA came in 58 and the first director of NASA was the Hollywood director of Paramount and Goldwyn Mayer, because the first director of NASA was this guy, T. Keith Glennon. He was the director of the studios of Paramount and Goldwyn Mayer. Most people don't know this. Well, then they started to make a show out of space science, space exploration. It was a show. The Russians were in on it with the Sputnik. They were the first to send the first satellites, apparently in space. And it went beep, 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 beep around Earth, and everyone was scared to hell because they said the Russians could put an atomic bomb on the Sputnik and drop it anywhere in America. So it was a fear-mongering thing. And then the space race started, and American tried to put the first satellites with the Vanguard. It exploded on the pad, and then the second exploded on the pad. Oh my dear, the Americans are incapable to launch a satellite. So if you just study this recent history, you can see it's a Hollywood narrative. It's a completely nothing to do with science at all. It's a thing for the public, for the masses to buy into. We have to stop this joke. It's a huge, enormous money-making joke, and it's a Ponzi scheme. They're taking money from the taxpayers to make NASA run, and not only NASA, as Anastasia said, they're doing it in China, they're doing it in Israel, they're doing it in India, they're doing it now, of course, but they're not doing it everywhere. I mean, we in Sweden, we're a pretty advanced country, right? We're an advanced country in Sweden. My birth nation, but we don't have a space agency. Why? Why doesn't England have a really fat ass space agency? Well, it's only America and a few others that are playing around with people's minds. But you see, now we are digressing. We want to stay on track, right? I mean, I would like to, because it doesn't matter if I'm wrong about this. It doesn't matter if you believe or you don't believe that we have that rockets can work in space, because they can't. Well, they can't, because that's the first law of thermodynamics.
Sweden
The
actually
Joule
does have a
expansion law.
space
The Joule
agency.
expansion law dictates that if you release, a strong gas in a vacuum, there will be no work. No work will be done. So when you have a rocket going up in the air, it will be going very nicely for 100 kilometers up to the common line. It will push very well, like fireworks. They work very well. But once they meet the total, void, the vacuum of space, they stop ascending because gravity exists. You're a gravity denier if you think that rockets will continue to push on nothing. You're against Newton's third law. Newton's third law says
They're
that an
not
action
pushing on.
is a
They're
reaction.
pushing.
When the reaction subsides, there can be no action. So they discovered this in the 30s. I've been reading some interesting old articles from the 30s. They were trying to see how far they could launch rockets. They wouldn't go far at all, and they were desperate to make them go further. They had these plans to go to the moon, but they obviously realized it was impossible. So they took over. Hollywood took over. Hollywood took over and said, "We can make money of this." That's my interpretation of has been going on in my life. Okay, and I'm a pretty, I'm pretty, I'm a guy who questions things, and of course, I didn't realize NASA was fake until it was pretty old, and it took me a long time to even consider the idea that NASA was a total Hollywood department, but it is in my mind. So once we take this the NASA stuff away, you will see how many things that you think that physics have been proven that just disappear, and we need to start from scratch. And we have geometry, and we have observations to work with. And the Tychos is the first step. I believe it's just a first step to reconstruct. I mean, you're calling yourself demystify science, right? Well, that's what we need to do.
So I have a
We need
question.
to demystify science.
I have a question. Is there any piece of evidence that would change your mind about whether or not we've gone to space?
Is there?
Is there a piece of evidence that you could be presented that would change your mind to believing that we've gone to space?
Well, you see, I have had a forum for many years, and everyone was free to show their own evidence. I started in 2009, and I've been writing like hundreds of articles and research about NASA. Everyone was free to show me. No one has been able to. So yes, please go to my Clues forum. And
I think what Nasti is asking is like, what would that look like? Like, what evidence would you accept as evidence that we've been to Jupiter, that we've been to Venus? Like, what would convince you of that in your wildest imagination? Like, what can you imagine some scientist coming to you and showing you that would make you believe it?
It's a question I could simply just bounce back at you. Show me the evidence that they have been. It's a funny question.
Well, there's ample evidence. There's ample evidence that they have been.
I have so much evidence in my. If you like to see my evidence, it's there. It's published. It's on the Clues forum. It's hundreds and hundreds of small, different various investigations, especially photographic, because they use fake. They use CGI, use photographic tricks, and there are hundreds of what I call evidence thesis.
The fact remains, right? So it's like if a conviction is not ideological, then presumably there is some evidence that, if presented, would lead you to change your mind. That's like the difference between a scientific viewpoint and an ideological viewpoint.
But I would love to have someone present it. So be the first one, if you like. I mean, I would certainly listen to. I'm not someone who closes my ears.
If images are not acceptable, if association with people who have launched satellites is unacceptable, if telemetry data is unacceptable, like what category of data that has not yet been collected? Like, would you have to go in a rocket ship yourself to go to Mars or something?
At this stage, yes, I probably
Okay.
would have to have go to a rocket ship myself, because I don't believe a rocket can exit the atmosphere. It can go beyond the Kármán line, where the atmosphere is, I think it's 22 million times thinner than at sea level.
I think all we have
And
to do
you,
is raise like $20 million and we can start a Kickstarter to get Simon up to space.
Yeah, because you can take rides
oh, I
to
love it.
space,
Oh, love
right?
it. Oh, yeah. Well,
I think we should
I'll give
seriously
it a go.
consider
Kickstarter.
this.
Okay, I'll give it a go.
Donate.
I want to see the Tycho crater up close, the Tycho
Okay.
crater on the moon. So send me to the moon, and I will go walk around with I will drive around with a rover around the Tycho crater. I mean, guys, don't you see how ridiculous these stories have been all over the years? Why would they send 3 rovers to go a few kilometers around the moon? It's so stupid. The narratives are so ridiculous. I tell you one thing. Here in Italy, like 10 years ago, everyone was still believing in moon landings. Now I think it's less than 50%. There is an explosion going on. And I'm not talking about flat earthers. It's not flat earth. The flat earth movement was launched by NASA itself, because they want to associate people who doubt NASA with idiots who think the earth is flat. That's my simple explanation of the existence of the flat earth thing. It is obviously designed to make everyone dismiss anyone who questions NASA. And it works perfectly well. I mean, there are thousands of flat earthers around the world now. And it started in 2015, just when we were showing that even the Challenger disaster was a hoax, where those 6 astronauts are still alive. That was my own research, and I never took any credit for it. But
I mean, why do you like for me? It's like, how do you if look like conspiracies tend to work best when they're small, when you only have a few people involved who are working on it, because it's really hard to get people to keep their mouth shut, basically.
yeah, just like
But when
Santa
you're talking
Claus,
about
yeah,
like multiple countries and hundreds of thousands of employees and
yeah.
how can you? It's just it's hard for me to understand
Michael,
how such a
you remind me of the funniest meme I've ever saw on somewhere, Facebook, I think. It's a mother talking with her child, and the child is saying, "Mother, is Santa Claus fake?" And she says, "Oh no, darling. Too many people would have been in on it. Would have had to be would have to be in on it. Too many people would have to be in on it on the Santa Claus joke." Well, most children are born with the idea that Santa Claus is real, and then finally they get over it and they accept that it was a fable. The same thing has to happen with adults. That's all I'm saying. Too many people is not an argument. Too many people is not an argument when you have a government of the most powerful nation in the world, like America and Russia and the rest, all those mafia people who govern us. Nothing is too big to folks. The bigger the lie, the better it works. That's the truth. The huger the lie, the more people will buy it, because it's official. It's everyone believes the same, so I must believe the same. You gotta get over it. It's not being a conspiracy theorist, it's being a realist. It's being an intelligent person, taking finally in their hands the hoaxes that are all around us. I mean, you must have noticed some at least. I mean,
oh yeah.
I hope you didn't take this, for instance. That was a huge international hoax. Everyone, every medical institution was in it, obviously. And people died because of the
I really wish you hadn't mentioned that, because we can't talk about that on YouTube, unfortunately.
it doesn't matter if you don't agree with me, but if you at least could you cite at least one thing that may have made you said, that doesn't sound true to me. Is there anything in your modern world, in the world where you live in, that you have questioned?
I think there are most things, I would say, that we
Okay.
question. Like we had the very disorienting experience of teaching immunology during the peak of the event. I know.
God, we have to
I'll
edit all
slice
this out because we can't talk about it on YouTube.
But the point is that like we were teaching immunology of. We were looking through all of the primary research papers and watching what was happening externally versus internally and seeing this massive disparity. And, you know, there's lots of other stuff like if you look at stuff like the Big Bang, if you look at the way that we conceptualize the structure of stars, if you look at I mean, honestly, I think a lot of the AI stuff that's happening right now is also pretty nonsensical.
It's also been like enormous lies in the past, right? Like
huge.
the Gulf of Tonkin business.
I mean, I was suspicious of
Pearl Harbor.
9/11 from
Pearl Harbor has
basically
been
the age
completely-
of. What's
Well,
that?
at least like
Harbor.
they've admitted to the Gulf of Tonkin. I mean, there's huge lies that definitely get perpetrated and people don't seem to care, right? I mean, Vietnam was a disaster, and it's pretty well known that it was based on a complete fabrication. There never was this Gulf of Tonkin incident.
Yes.
So it's like, look, governments are definitely capable of lying, like for sure, hands down. That's why I say I'm open to this. I just personally feel like, you know, at the beginning of the conversation, you're like, why won't anybody take this model seriously? And I'm like, well, you know, even if you didn't believe it in the Newtonian equations, it would be really cool if you could find a way to map those reported masses onto your model. I think it would open up everybody's eyes to this model, and you wouldn't have, because look, the minute you tell people that like NASA's every single space expedition is fake, it's like there's probably 100 people on the internet who are willing to entertain that idea.
That are
No.
scientifically literate enough to also be
I
considering.
beg to disagree, Michael. I beg to disagree. It's only a question of time before this will not be so again, because
I'm just saying, even if it's true that that all of the space data is garbage, like just completely fabricated, even if that is true, it would go a long way to opening up people's minds to this model if you could rectify the mass balance between these different planets. That's all I'm saying. I'm like, it would be an exercise that would probably take you a year.
Saying that, Michael, you've been saying it's 5 times now. That the mass thing is the thing we have to. Why is that? Why do I have to show that the Tychos agrees with the equations of mass which have been built around a wrong geometry of a solar system?
No,
Because
they're built on Earth
what you would have,
primarily.
and the reason that you have to do that is because if you throw out Newton's gravitational relationship, you have to replace it with something.
Fine.
Like
So,
ideas
okay.
are accepted when there is so you look at an old idea, you're like, this old idea doesn't work.
Okay.
I have recalculated it. This is what this actually works like, and you come up with another relationship that's actually able to do something. Like they use.
It also seems to be pretty well established on Earth, right? Like the Cavendish experiments, like they can do these torsion balances. They can calculate the masses on small scales. Like all of the Newtonian equations work, as far as we can tell here,
So
and they
let me
work.
put this so let me put this another way, then, Michael. You said earlier on that you were amazed at how well the Tychosium works with observations. So here we already have something that works, even though the whole dynamics, the celestial dynamics, are different. So why wouldn't we be able to arrive and to understand what kind of, at what crossroads did we go wrong? And maybe the Newtonian, I mean, I even say that in my book, even the Newtonian gravitational laws might be rescued if we just look at it the other way. They may be right too.
That's what I'm trying to point out.
I'm not saying in my book, I'm not saying in my book that we have to absolutely discard everything that Newton did, for instance, or such things. What I'm saying is, let's look at the geometry first and see why does it work better? Because it does. It does. That is no question about it, that the geometry works better because it agrees with the positions of our planets with the stars. And that is not the case with Copernican simulators. It is not the case. If you have a simulator similar to the Tychosium, that is with a top view or a 3D view of our solar system, they can't put stars in the right places without having to say, yeah, when we are on the other side of our orbit around the Earth, we still are in front of this star because the star is so far away. So there will be no parallax detectable. Well, we have been moving 300 million kilometers, apparently. according to them. So 300 million kilometers will still make us face that same star. Come on, why? They always reply, because the star is so far away. So maybe just a question of, well, it's not a good excuse. We show in the Tychos that when Mars comes back, because Mars does this funny thing, Mars returns facing the same stars 7 times in 707 days. But the 8th time, it only takes 546 days. Try to explain that with a Copernican model. You won't be able to. It's impossible.
Simon.
Anastasia, I finish. This is one of the strongest part of the Tychos. The Tychos model shows that this is exactly what is to be expected with Mars. Mars will return here. This one. You see this? This.
Yeah. So you basically have the Earth-Sun system, and then you have the orbit of Mars in this concentric spiral pattern.
This graphic is fundamental. This is one of the biggest, evidence we have at the beginning of the book. We show here. When I say we, it's me and Patrick. We're two guys. We show here that Mars behaves exactly as it is observed in the Tychosium. That means that it returns facing a given star. We chose this control star Denebel-Jedi, and look, Mars returns exactly on the same line of sight each time. But how do they explain this in the Copernican system? In the Copernican system, Earth and Mars would be here on this date. And on this other date, the short empirical interval, sidereal interval, we will be on the other side of our orbit and still be facing the Nebel-Jedi. This is.
I mean, presumably because it's so freaking far away that
there you go. Okay. Presumably, no, because now they're saying that they have the incredible precision in their parallax measurements. They have 0.000001 error margin with their Hipparcos satellites. So they can't say that anymore. You understand? They cannot take this. They could have said that 100 years ago. Oh, the excuse, well, our telescopes can't see this little. No, they can't do that anymore. You understand?
That's something we actually didn't even...
And let me finish. I'm sorry if I'm interrupt you often. I'm sorry. But if you say that, okay, maybe this could happen. Maybe this that happens in the Copernican model could happen. But then you would have to go back to the Tychos and say, the reason why this happens is just a complete coincidence. The reason why it works in the Tychosium, that is that Mars returns 7 times in 707 days and the 8th time in 546, is just a question of coincidence. You want to argue that in front of a court of science? You want to argue that?
No,
this is the only model that works. This is the only model that works exactly. It shows why Mars returns on the same line of sight in this funny cycle that is empirically verifiable. And Kepler, you know what Kepler did? Kepler averaged these 8 numbers. He just averaged them, and he got 689 days. Well, at no time does the Mars realign with the same star in 689 days. Never. It always realigns even 707 days, approximately, and the 8th time in 546. So Kepler was a fudger. He fudged them numbers. His war on Mars, which he took 8 years to complete, and he never actually found the solution, was it was an impossible quest. It was doomed to failure.
Yeah, this reminds me of I wanted to ask you about some of this parallax stuff, actually. So in the Tychos model, you have this different baseline, right? It's a much smaller baseline, which means that the stars are way closer than we normally hear about in mainstream astronomy.
42,000 times closer.
Thousands of times. 40-something.
42,633 times.
What does that mean about some of these stars that are, like, because there's at least one star in the ephemeris that's supposed to be like 1 light year, but
4.5.
4.5. There's this one from the paper. Well, it doesn't matter. Even 4 light years away,
Alpha, right? So Proxima Centauri, the closest star. Okay, the closest star we have, Proxima, is supposed to be 4.2 light years away, right?
Sure. So what does that mean? Shouldn't it be basically on top of us then?
No, it would be between Saturn and Jupiter. And Tycho Brahe famously said, I think the star starts right around Saturn. The stars should be starting there. The first star should be around Saturn. And this is exactly what we have in the Tychos. The closest star, Proxima, would be, let me see if I can find it in the book here.
By the way, I was thinking about, so you referenced this paper in your book by Goretti, and he measures this star GSC 3573-129 to be only a light year away. And I don't know if other people have followed up on that, but even 4 light years, you're talking about, so there's basically these stars are really close. Some of them are closer than the planets. How do those...
Only very few would be closer than the planets. And why would that be so strange? We have
do they affect the orbits then?
We have millions of asteroids. We even have binary asteroids we have discovered in later years. There is nothing strange of having stars. They're just certainly much smaller than we think. Being around the distance to Saturn. Saturn is very far away. It's not, it's not very close. So
wouldn't you expect like a huge parallax for a star that's that close?
Because we are moving at only 14,000 kilometers a year. So that's why the parallaxes are so small, and why it took so long time for all the astronomers to discover one.
And so, is there no? Wouldn't there be some kind of so early on in your book, you basically say that you leave Einsteinian and Newtonian physics at the door, and so this model is purely geometrical because it doesn't have gravitational mechanics in it, and so it works on the basis of this star that's supposed to be between Saturn and Jupiter, not affecting anything gravitationally, right? Because it's not part of the Tychosium simulator.
Yes, well, I just so when I say leave it at the door, just momentarily, just leave these dogmas at the door momentarily, because we have a new thing to look at now. We have a geometric model which works better, and then therefore we have to leave it at the door for a while. Some assumptions that have been done. Since we talked about the sun, Michael mentioned we all know that the sun is huge, and yes, of course, we know it's huge. But we also are told, and I think it's true, right, that the sun is made of 98% helium and hydrogen. Well, those two gases are the lightest gases known to man. So if you would put the sun on a bathroom scale, imagine in a fantasy world, you put the sun, it might even weigh the same weight as Mars, which is full of iron and rock. Just 205 times different in size, but the sun is just made of the lightest gases we know, and they're even burning, and gases burning are even lighter.
Definitely doesn't look like a gas to me, but that's just me, I suppose.
So you are questioning the official explanation of what the sun is composed of. It's composed of 98% helium and hydrogen.
No, I think the elemental analysis is correct based on the spectroscopy.
Right.
I just don't think that it's in a gas.
Why would it be so heavy? And then on the other hand, they say officially that the mass of the sun makes up 99.8% of the whole mass of the system. That doesn't sound right to me.
By the way,
why would the sun be such an incredibly predominant thing? Mind you, the sun is important in the Tychos, because I'm saying the sun is like the central magnet. But why do we need to talk about masses and weights? We have never put any planet on a bathroom scale. Sorry if I repeat this analogy with a bathroom scale, but we have never verified this.
Well, yeah, I mean, you'd have to bring in satellites, right? You'd have to bring in space data.
Only equations have come up with the theories we have now. No direct verification, because it is obviously impossible to verify the weight of a planet or a star.
Well, you have to go there, right? So if you don't accept that we've been there,
Even
it's
if
very
you go
difficult.
there, how do we put it on a bottom scale? Sorry if I talk like
you have to look
it.
at the deflection of the.
But
I
by
talk
the
like
way,
a child, but, you know.
I was like, I've been calculating the apparent parallax that you would expect from, what is it, Deneb Algeri was the star?
Yeah, the Nebeljet is quite.
Like
quite,
it's supposed to
distinct
be
star.
40 million 40 light years away. 40 light years away is
Yeah.
2 times 10 to the 14 miles.
Mm-hmm.
And the angle that you would expect for that parallax is 2 times 10 to the negative 11th degrees.
Yeah.
And so it's like the fact that the fact that you can travel 300,000 kilometers from one end of the orbit to the other and then see Mars and Deneb Algeri and Earth align doesn't, like the distance that it's supposed to be at lines
No,
up.
that's not work necessarily. No, I know exactly what you're saying. I mean, I've heard this 100 times. No, it does not work like that way.
Why? I mean, this is just geometry, right?
Deneb Algeri, if we can see Deneb Algeri right on a hairline's breadth of thing on both occasions, and we are supposedly 300 million kilometers apart, so they are practically parallel loose lines, and they are parallel they are absolutely parallel on the Copernicus images. So in that case, Deneb Algeri would have to be 300 million kilometers wide at least. But no one is saying that Deneb Algeri is 300 million kilometers wide.
Wait, why would it have to be? I don't understand that.
Because in order to see it on the same line of sight.
I think Nasi is just saying that the angle is so shallow that you can't really resolve the differences.
Well, look, do you know how do you know how Cassini and Richer, his colleague, measured the parallax of Mars in order to establish how far the sun was away, how far the sun is? They just took the 7,000 kilometers between Paris and Cayenne in South America, and they saw a very distinct parallax of Mars with the stars.
But Mars is way closer than 40 light years.
Yes, of course. So that was easy to do, but it will work the same. You see, I mean, just go. I encourage you to look at the distances to the various stars which we know. You know, take the 10 most famous stars and look at what they're claiming, how far they are.
I mean, man, I hope you're right, because then we can go visit
the
the stars.
official explanation as to why we see them with our naked eyes, because we could not possibly see them with our naked eyes if they were that far away, because the sun is only 0.5 degrees in the sky. You know how big the sun is? It looks huge to us, right? We used to think the sun is huge. No, if you take an old vinyl record, 33 RPM record, right? Take an old record and stretch it at arms outstretched. You stretch your arms out with the record in your two hands. Well, the sun will only fill the little dots in the middle, the hole of this vinyl record. That's how small the sun is. Well, they're telling us that Sirius, for instance, is 500,000 times smaller. Yet we can see Sirius very well. It's a huge, very bright star. And Tycho Brahe estimated it to be 16 times smaller than the sun, not 500,000 times. Okay, so how do they explain that? Oh, that's because of refraction, because only the stars are affected by refraction, because the light that comes from the stars is enlarged, inflated by the atmosphere. Yeah, but why wouldn't Jupiter look 100,000 times larger than it is then? Jupiter also, the light from Jupiter has to traverse our atmosphere, right? No. Only the stars suffer this incredible inflation of their apparent size. It's ridiculous, folks.
Well, Jupiter barely releases any
ridiculous.
light.
The size of the stars, you can see. Have you ever seen Sirius in excellent conditions? It's very huge, guys. It's huge. It's a huge thing, and it's certainly 16 times only smaller than the sun, like Tycho Brahe expertly estimated. He was an expert, Tycho Brahe. he said it was 16 times smaller only than the sun's disk. And they're saying 550,000 times. So they are absolutely out on the sea. Those astronomers who are accepting the distances of the stars. It's absolutely ridiculous to think they are so far away. Has absolutely no.
I mean, it's very, very hard
no
just on the
relationship
brightness of a light to be
reality.
able to. It's very difficult. Like if I'm walking down the street and a car is coming towards me, it's very difficult for me to tell whether it's just a tiny little motorbike or whether it's a huge semi truck, and they're just at different distances from me. This is a huge, long-standing problem, and so you end up with the mass luminosity relationship. And
it's hard. Yeah,
I mean, I agree. This is very difficult. But
they're sure they are absolutely right. That's it.
But where did this 150 x factor? Because I'm looking, and the diameter of Sirius is twice the size of the sun.
It comes from.
This,
I mean, you need to read my book. You haven't read my book.
I have. I've.
No.
I have it here. I have. I'm cross-referencing the things that are in the book.
Where I say 550 because you have to understand. 550, I think it is. Let's see. They are okay, more or less 550,000 times. I must find the exact number so I can convince you about that. They are saying, okay, basically they're saying that the apparent angular diameter of Sirius is 0.0. Let me see if I can find it in a search. 0. What is it now? 5 something. Oh, it's not here. It's in another chapter or book. All right, of course, it's on the stars or the stars closer and believe. Yeah. So let's see now. 550. Yeah. All right. Here. Okay. Do you see my screen? The heliocentric.
Yeah. Which chapter is this?
This is chapter 23. Chapter 23. So the heliocentric absurd claim that Sirius is located a whopping 550,000 times farther away than the Sun, or 88,000 times farther away than Jupiter. These are numbers that are verifiable. You go to any place which tells you how big they think the real angular diameter of Sirius is, and they will tell you it's 0.0593 or something. With me, 0.05. I mean, something extremely small.
0.0056%.
0.005936 is, according to them, the true angular diameter of Sirius. This number is extremely small number, and that corresponds to 550,000 times less than the Sun.
I think that's Sirius A, not Sirius B. Or sorry, that's Sirius B, not Sirius A. Sirius A is...
Of course, we're talking about Sirius A. We're talking about the biggest star in the sky, yes.
Yeah, no, what I'm saying is that the diameter of Sirius A is twice as big as the Sun.
No.
Yeah, I don't know what to tell you.
Yes.
Are you reading that off Wikipedia, Nastya?
Yeah.
We have,
like, I'm
yes, it's 1.7. Anastasia, we have to differentiate two things.
Okay.
They say that in reality, Sirius A is 1.711 times larger than the Sun. Yes.
Okay.
Not twice, but 1.7.
Sure.
Yes, in reality. But what they see in their telescopes, and that's the funny thing. That's what we're talking about here. In spite of Sirius being, twice the Sun, in their telescopes, they see, no one sees it as small as this, 0.0, but they say that 0.005936 is the true angular diameter if you just remove the airy disk. The airy disk should be, this effect that inflates the dots of lights we call stars. So for some strange calculations, they reduce because they need to reduce them because they want them to be so far away. Of course, the Sirius does not look as small in a telescope. Sirius looks in a telescope like 1/16 of the sun. Just
Well,
like
it
Tycho Brahe
depends on
saw
the
it.
size of the telescope, right?
Tycho Brahe had no telescope, but he had very, 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 very accurate instruments. Otherwise, he would not have been able to do such incredibly accurate measurements up to, 1 arc second or 1 arc minute, or even better. So Tycho Brahe knew what he was talking about, and he said that Sirius was just 1/16 of the sun. They are saying it's one out of 550,000 times. So
I can't find that to be the estimated diameter of Sirius. Like the estimated diameter of Sirius is given as
you think I've not been looking for? I mean, for all these years I've been looking. I'm telling you, these are the numbers that we have. They are saying again that Sirius. Look at this picture here. This is a photograph, a pretty good quality photograph, right?
sure.
So on the far right, you can see Sirius, right here.
Yep.
And here you can see the moon, right? Okay. How much smaller do you estimate with your own eyes is Sirius in comparison to the moon? And remember, the moon is the same size as the sun in the sky, 0.5 degrees. Right? So we could even think that of this like the sun. It is the moon, but it could be the sun. Well, does Sirius look 550,000 times smaller than the sun? No. Oh, people will tell you that's because, well, they will tell you because it's because of the refraction of the atmosphere, which we make all the stars look so much larger than they are in reality. Do you follow me? This is what they are saying. I mean, I'm not a crazy guy saying crazy things. They are. They are saying crazy things.
I don't necessarily think that anybody's crazy here. I think that
No,
this is
sorry if I use the word crazy, but it is absolutely crazy to say that the biggest star we have in the sky, the most spectacularly big star in the sky, is 500,000 smaller than the sun, which is only 0.5 degrees. Yes, it is crazy to say that. Sorry. It's not crazy. It's almost it's insane.
But I mean, if that star was at the same distance as the moon, or sorry, as this, if Sirius was at the same distance as the sun, let's say we replace the sun with Sirius.
Yeah.
How big do you think it would be in the sky? You think that it
1.7 times? It's probably
Okay.
it could very well be correct. It could well be correct, and that's explained also in the chapter about Sirius. I'm not saying that because of my estimate of the stars being closer, that does mean necessarily that the stars are much smaller. No, they can still be, as they say. I mean, their real sizes, officially defined sizes, could still be valid, but the problem is how they gauge the apparent size of the stars as seen by the naked eye or in the telescopes. That is absolutely, that doesn't work for me.
I mean, I think that there are problems with mass luminosity. And since mass luminosity has a lot to do with apparent size, then obviously there's some issues with that.
Okay, so luminosity. You wanna talk about luminosity? So they're saying that Sirius has a luminosity like like a wattage of a bulb. No? Luminosity is basically that. Right? You have a bulb in your kitchen. You change it from 60 watts and to 120, you get twice the light, right? Well, they say that Sirius has about twice the. No. They say that Sirius has 25 times the luminosity of the sun. Well, what do you know? I'm saying that Sirius is maybe twice the size of the sun in reality, but it is at 12.9 AU. So like 13 times further away than the sun. So 13 by 2 is 26. So maybe what they are seeing is that the luminosity that they calculate for Sirius is Sirius is 25 times stronger. His wattage of Sirius 25 times stronger is because it is 1.7 times or twice the sun. It is in reality. But you see, if it is in reality as close as I say, 13 AU, that is 13 times further away than the sun, that would make sense because 13 times 2, 26. So what I'm saying is that Sirius has the exact same luminosity as the sun. Because why would luminosities from one star to the other change? Why wouldn't all the stars have the same luminosity? Do they have all different kind of fusion processes that make them shine stronger than the others?
Well,
Yeah,
the standard idea is that they're bigger. I mean,
no, they're
more
saying
stuff.
That, no,
yeah.
it's not only a question of size. Some they say that the Deneb, which is one of the brightest stars we can see with our naked eyes, they are not sure, but they say it has 196,000 times the luminosity of the sun. And some other websites say no, it has 233,000. They don't even agree. They are just shooting out numbers like that. But they're saying that Deneb, the reason we say Deneb, in spite of Deneb being like 3,000 light years away, 3,000 light years away, you know what that is? We can still see it with our naked eyes because its luminosity is exceptional. So they are completely
we can't confuse so apparent brightness is what you see. Luminosity factors in the assumed distance in the first place. So you can't, it's like what I was given that example about like walking down the street. Something can appear really bright, but it's really just a little motorbike that's about to hit me in the face, right?
Yeah.
So you have to assume a distance in order to actually achieve the luminosity. And from that, then the theory is that will give you the mass of the star as a result of it. But it does assume a distance in the first place, which is presumably calculated by any number of different means. But we're talking about parallax here.
And I think that it is perfectly reasonable to suspect that the mass-luminosity relationship is not giving us the correct distances. But when I look at the Tychosium, I see a geometric system that works perfectly, that doesn't have gravity involved in it. Because if you have these stars that are so close in, they should also be part of the simulation. They have to be affecting the motion of the planets. And a star that's between Saturn and Jupiter would be affecting everything that's nearby it because it's so large.
Anastasia, why do you assume that? Why are you so invested in the idea that
gravity exists?
Gravity would
Recurs.
do so much effect on the surrounding bodies. We have never really.
It's keep me on the ground right now.
Everyone is saying, yeah, it's been proven, No, it's not being proven. It's not being proven, and they have problems with that. And again, I don't want to go back to the galaxies, but they have huge problems with what we see is going on in the galaxies, and they have to come up with dark matter, which no one knows what it is. 75% of all the matter in the universe should be dark matter, invisible stuff. I mean, it's pretty funny. It's pretty laughable.
Well, so actually, I think that with the dark matter thing, you mentioned in your book Walensky's stellar metamorphosis.
Yeah, Jeff's a friend of ours.
And I think that stellar metamorphosis is a wholly plausible theory where the universe is trillions of years old, and so you just have all this cold, dead stuff that's floating around that gets sent to the outside of the galaxies, and then you solve the galactic rotation problem because there's just cold stuff that you can't see, and so you're like, my god, there's dark matter, but in reality it's just detritus.
Dead stars.
Like the same way that you go to the beach and you look at all the foam at the edges of the waves. Like there's just a bunch of stuff.
Yeah, it could be. Yeah, it makes a pretty good sense, doesn't it? So I've not been studying very profoundly Walensky's theory, but strangely enough, he's never come back to me. I would like to talk to this guy.
He would love to hear from you.
Yeah, I think it's possible that even our Earth was an old star, because what do we have in the middle of Earth? We have magma that sometimes spurts out of the volcanoes, for God's sake. Couldn't that be the remnant of
It's
an old
interesting. It
star?
was, the first place I saw this written about was by the Soviet scientist Oparin back in the 60s, because the Soviets had a very separate sphere of science from the West. And so this idea that the Earth used to be a star is actually was taken quite seriously, as far as I can tell, in the Soviet Union. And it actually goes way back before that. You can find you go all the way back to Aristotle in his book Meteorology. He writes that the planets are stars, and there's no real distinction.
Right.
So it's an old idea. It's been around for a long time.
Michael, you just mentioned the Soviet Union. Can I say something? Can I do a scoop here for you?
Please.
Yeah, hit it.
A Russian version of my book is about to come out. A guy in Russia, Alexander, has been translating the whole Tychos book, and I am feverishly changing all my graphic captions to Russian, and it's a long, hard work. This is what I'm doing these days, and I'm looking forward for this this book to come out in Russia, because I have a feeling that the Russians are a bit more open-minded on scientific questions. They've always been.
Definitely.
So I'm really looking forward. I'm very excited to see the book coming out. The guy says he has some contacts with publishers. He's an extremely well read guy. He's obviously knows astronomy very well. He's so rigorous, and he's just making it so easy for me to get this book in Russian. He's doing everything, and he's incredibly, he's working very hard.
That's cool. And half our family is Russian, so there you go.
We have a Russian Tychos book.
That's pretty amazing. I mean, getting a book translated to another language is
especially
a feat.
Russian.
Why? Just because it's so difficult?
It's like the hardest language I've ever failed at learning.
I mean, the Cyrillic alphabet, it's unfortunately very much longer. The words are very much longer, so I'm having a really hard time to make it fit into my graphics.
Whenever we're watching movies, like Nastya speaks Russian, and I'll be like, "What did he just say?" And she'll be like, "He said, it sounds good." I'm like, that was like 3 paragraphs worth of speaking. How is that possible? But
I mean, look, I think that this is a really, really interesting model, and it sheds a lot of light on the way that science operates, which is that you can look at the same collection of data points and you can come up with completely different mechanics for how you fit them together. And
but the world can only stomach one at a time. That's the really fascinating piece of it.
Well, let's be clear. I think that the only reason that the world can only stomach one at a time here is because of the gravity question. Like that's literally, I think that if Newtonian gravity could be included in this model would have,
I think it'd be a slam dunk.
It would be a slam dunk.
Yeah.
Like it just, and for me, I always like to see these ideas that are kind of out there or unconventional get more play get more play. I want people to be thinking about them. I want people to be considering them. And so it's like, what would it take to be able to include gravity in Tychos?
Sure. Can I just point out one more thing? Maybe time is running out, but Mercury and Venus, I'm saying they are the moons of the sun because they are obviously the moons of the sun for many reasons. But let me tell you just one reason. The rotational speed, equatorial rotational speed of Mercury and Venus just happen to be walking pace, 2.7 kilometers an hour and 5.4. So, and one is twice the other, and another 3 times is the rotation speed of our moon, 16 kilometers an hour. So our moon rotates very slowly at 16 kilometers an hour. You understand? 16. It's like going on a bicycle very slowly. And Venus and only Venus and Mercury have even slower rotational speeds. Every other planet has speeds, Neptune 47,000 kilometers an hour, Saturn 35,000. How is it possible that all the astronomers of the ages have never realized that Venus and Mercury are very particular things? I mean, they rotate very slowly around their axis. completely unlike all the others. Why? Because they are tidally locked. They're tidally locked to their host, the sun, and we are tidally locked to the Earth, and that's why they rotate slowly. That's the definition of the moon. And also another mystery that even you read it in the biggest astronomy books. The reason why Venus and Mercury don't have moons is a mystery for scientists to solve. That's what they're telling you today. I mean, ask if a kid asks you, "Hey, Anastasia, do you know why the moons don't have moons? Why Mercury and Venus don't have moons?" You wouldn't be able to reply to them because it's a mystery. I'm just telling you they don't have moons because they are moons. And if you go to some Wikipedia place again, they will tell you that no moons have ever been observed to have moons of themselves. Now, no moons of Saturn have moons, no moons of Jupiter have moons. Okay, so moons don't have moons of their own. You don't have a moon going around on a moon, not a moon. So obviously Venus and Mercury have moons, and they rotate extremely slowly. No other planets rotate that slowly. How is it possible that no one has discussed this thing before? For all of these hundreds of years.
I mean, I like the model. Like I think that it's very important to put down on the table that I think the model is one of the coolest models that we have come across in the 3.5 years that we've been doing this project.
It works. You see, it works.
So this brings me back to the question that I had earlier, which is, what would it take to include gravity in this simulation? Like, is that...
Let it come. Let someone help us out. I mean, I'm open to anyone who wants to do that. It might even be that we find out that gravity as we know it works as well, just as well as the ephemerides work now. Because the what ephemerides are? The positions of the planets over hundreds and hundreds of years. They're exactly the same. They're practically the same on the stellarium, official planetarium, and on this one. Because you can go any place you want, and you will find Venus being right there in 3,345 BC. You will see Venus there.
And that's what's so crazy about this model. Like that's the best and most incredible part of this entire thing, which is that it works so well. Like we didn't get into the comets, but you have the orbit of the comets, and you have the weird thing where when Halley's comet comes in, it shows up with this shrunken periodicity due to its what's the trochoidal orbit.
You mentioned Halley's comet. I mean,
you're opening a can of worms with that. I don't know that we have time to do Halley's comet right now.
No, we don't have the time. But just very briefly, Halley's comet is the last nail in the coffin of the Copernican system. I tell you.
Yeah, can you pull that chapter up so that we can show people what that looks like? Because I think that the that visualization of the odd periodicity of it is really, really interesting. I hope that you don't take offense at the fact that I have so many questions.
No, not at all. Not at all. I'm craving for people making questions. I don't like people who say, "Yeah, nice, Simon, well done."
Good, we're the same then.
I absolutely want questions, and I want to be challenged because I'm ready, and I find it very exciting.
Hey, so something that I noticed while we've been doing this is that you have a version of the Tychos book at tychos.info, which has all the chapters laid out, but they don't seem to align to what's in the printed book. And you're looking at a version of it that's different than that yellow background version.
The yellow background is the first edition.
I see. So book.tychos.space.
Forget tychos.info. That's old.
Got it. Okay. Okay.
This is the one you want to go. Now, actually, only a month ago, I finished to we have been working so hard with a proofreader, Jesper in Brazil, who is he's half American. He's done a proof. So I finally made the Tychos space open website identical to the book, but it's a second edition. Forget the yellow background book. That's a Tychos info. Don't go there again.
Very confusing.
I think I'm going to close it down because people Google pulls up the Tychos info, my old one before this one.
You could probably just do a redirect.
Yeah, I'm trying to understand how to do it. So anyway, Halley is an incredible thing that I absolutely didn't expect to discover. It was all Patrick's fault, because Patrick, he likes to discuss with lots of people, and he always challenges people around the world. And once he challenged two Swedish guys on Reddit, and they told him, "I bet your Tychosium cannot put a comet, in the simulator." And he said, "Aha, really? Let's bet $100 about it." But he didn't tell me. So Patrick called me and said, "Oh, Simon, I've just been betting $100 with some guys that we can put a comet into the Tychosium." And I said, "What? Are you crazy? I'm not ready for this." But now we are laughing about it so much with Patrick. We're saying that was such a he gave me, he kicked me in my butt, and tried to make the comet fit in. And I used the same techniques I had used to, put Mars, Venus, all the same logic. And suddenly we had Halley circling around in the Tychosium. And we have now Tycho circling around in the Tychosium.
So basically, as far as I understand from what I've read, is that Halley's makes a pass, and then shortly afterwards, just a few months later, there's another comet that will appear, but it appears on the other side of Earth. So if Halley's is above the Earth, the next time that it passes, it's below the Earth. And the way that this is recorded in our models right now is that they're two different comets.
Yeah, it's always Halley's too. You understand? It's always
right. So Tychosium says that because of this trochoidal orbit, it's Halley's. But there is this weird coincidence that has never been fully addressed in the Copernican model, which is that why does Halley always show up with this other comet, which is always named something different? It's not like Halley has some companion that shows up. It's a totally different comet each time that just happens to show up a few months later.
So in chapter 30,
she always brings a new friend to the party.
Chapter 30 of my book is, one of the last chapters of the book, but it is the last chapter of the book. And it is all about Halley's comets. Why? Because, and it's the longest chapter of the book, because I wanted to show it, give definitive evidence of the fact that Halley's moves like this, like we say in the Tychos model. So let's see now. We will now see. Okay, this is Halley's arriving in 1986. There. Okay, 1986. Do you see the screen well now?
Yep.
Okay. So let's go back a week or two. Here. It comes right underneath the Earth. Okay, this was the last passage in the history of Halley's comets. Thing doesn't really work sometimes with the tracer. Like this is a trace of Halley. Okay, trace. So exactly on 1986, 26th of April, it didn't crash into Earth. This is just a graphic bug, okay? It didn't crash into Earth.
Not shown to scale.
It's a tiny thing, it's a tiny thing, so it's not crashing into Earth. So we'll have to do something about that in the next version of the Tychos. But anyway,
I like that it's like bigger. It's almost the size of the sun in this model.
Yeah. No, it's just to be able to see it, when you zoom out.
Course.
That's all. That you have constrictions when you do these graphics. Yeah. So, mind you, that day, what happened? The Chernobyl accident happened that day. just for the anecdote. Anyway. So
what was the accident?
The Chernobyl?
The Chernobyl accident.
In Ukraine.
Sorry, I heard a terrible accident. I didn't hear Chernobyl accident.
Chernobyl accident.
Oh, wow, that's wild.
Let's not go there. The thing is about Halley is that since it comes, revolving like this, let's go back a few months now. I'm going back month by month. Okay, you see where this is Halley here?
Mm-hmm.
So in 1983, with the good telescopes we had that day, we could have started, seeing Alice. Nobody saw it in 1983, but someone saw it in 1985. And Mr. Mackholtz, an amateur astronomer, saw it on May. In May, he saw it here. Okay. And but they gave the name of his observation of a new comet was it's now called the Mackholtz comet because it, according to their calculations, it could not have been Halley's because he wasn't expected to come where it is in this part of the sky. You see? I'm starting now from the last passage of Halley's. The last passage of Halley's had one guy observing a new comet appearing in May 1985, but he didn't say it was Halley's. He said, "That's my comet," and he even got a prize for it. He got a nice prize, astronomical prize for having discovered never be seen before comet. Never seen before comet. No, it was Halley's he was seeing approaching. He was seeing the approach of Halley's. And then finally he came, and everybody saw Halley's here with their naked eyes from the southern hemisphere, from South America. You see, they saw Halley's coming in 1986. So this is just an introduction to the concepts. So I've been going back every single passage, 76 years before, 76 years back in time, and checked if I could find in the books other instances of comets seen just 1 year before or just 1 year after. And I found 17 of them. 17 occasions in which those comets which arrived just 1 year before or just 1 year after Halley's were given other names. They were baptized with other names. But no, they were always Halley's. And I show it in chapter 30 perfectly because some of them were documented so well that they even had the ephemerides of that comet, unknown comet, and that corresponds to the place where it is in the Tychosium. Do you understand what we have here?
That's pretty cool.
We have something which cannot be debunked. I don't like the word debunked, but you cannot disprove this. I'm trying to make a conceptual explanation of the chapter 30, which is a long read, but please do read chapter 30. And it's like a thriller to read it, because I have been, like a Sherlock Holmes, I've been trying to find in different books. Did they find some comet in 1910 or 1909? Because in 1910 we saw Halley's. But did they find one in 1909, or did they find one in 1911? Yes. And every time I found some examples, and I document them in chapter 30. So what are you going to say about this research of mine? You can't say. It's an incredible series of coincidences.
It definitely is an incredible series of coincidences. I mean, that's the least you can say about it.
Yeah. I want to understand how, if you're throwing gravity out the window, what holds this entire system together?
Ask someone else. I'm not up to it.
You have to be. This is your system.
No, I'm just I mean, we all have specialties, specialties. I'm a specialized in geometry, and let the other people explain gravity again.
All right, so we're officially putting out the call. We need someone who can help get gravity into this, because
I say it in the beginning of my book. I don't have a theory of everything. I don't have a TOE. I don't pretend to have a theory of everything, but I propose a geometric configuration of a system that agrees with all observational data amassed and compiled by the best astronomers of the world. before NASA came on the scene. I completely ignore NASA because I really don't trust NASA, but let this be for another day. I mean, you can continue to believe in NASA and it won't change anything about Tychos, right? I mean, the Tychos is there. It agrees with hundreds of all astronomy books, which are extremely accurate and rigorous. Okay, so
there's no argument there.
Cancel modernity. We have entered an era of stupidity. The dumbing down of the people is on us. So we need to understand this. There were much more honest and earnest people before, like just 200 years ago. We're now surrounded by crooks and liars and profiteers and corrupt governments. We must accept this. It's
I mean, that's hard to argue with.
Yeah, I mean, look, I think this has been I think it's been a great presentation. I think that it's an awesome simulator that you guys built. Everybody, I'm sure by now, if you've made it this far into the podcast, you've probably checked it out, and it's pretty badass. There's so much to be drawn from this. Even if you're wrong, it's incredible what has come forth from this work. And so, I do agree with Nastia that this gravity mystery needs to be addressed, and I don't think it's beyond the work of people, scientists, other people listening to this podcast, you yourself, Simon. I think that this is a problem that can be addressed.
Is Patrick a mathematician, or what is he?
Mathematician, I wouldn't. Well, he's a programmer. He's extremely good in maths. Yeah, but
most programmers are sort of mathematicians.
Yeah, because I wonder if there's some mathematical way of conceptualizing gravity to fit into this.
I mean, we're not going to answer it today. No. That's the bottom line. It's like
no,
this is obviously,
this
is the first question that everybody's going to raise, and. Yeah. It's if it can be if you can answer that question immediately, I think it's just game over for the Copernican model if you can do that. If you can't do that and you have to just say, NASA's lying, I don't know that people are going to pay attention to this, even if NASA is lying. I just don't. I think it's people can't stomach that kind of upset to their world.
I know it is a hurdle, very, very strong hurdle to overcome.
And,
that's why I don't address it in the book. I don't talk much about that at all, actually.
That's fine.
I think that there is a psychological process that you have to follow in order to introduce new ideas to people. And those ideas they must be introduced in a specific way, and I haven't quite formulated how that works exactly. But I do think that even the most challenging idea can be wrapped in enough sugar that it can be transformative. It just really requires a delicate touch. And I think that it's possible. Like, you've assembled the evidence to an astonishing degree.
Yeah, kudos.
Anastasia, you asked me about when we started talking about Halley, you said Halley's passed above Earth and then below Earth.
Mm-hmm.
This is why it does it, because since its orbit is tilted by 18 degrees, this is what it will do when it comes close to us. It will come first above us. This is where Macaulay saw it coming here around May. He saw it coming above Earth, and then it made this loop, and then it came underneath Earth. And it was observed in the southern hemisphere. That's the last passage of Halley. So it all matches up. There's so many things that absolutely check out. And you know that if you calculate the width of this loop, it's 2 AU. It's the diameter of the sun's orbit. So obviously, Halley's comet is probably an ejectum. It's a piece of the sun that has been ejected, and by do you want to call it gravity or do you want to call
I
it?
think that
Or
would
do
be
you
the
wanna
right
call it-
direction.
I think
Or
from
do you
a
wanna- do you
political
wanna call
standpoint,
it,
yeah.
do you want to call it, what is it, other name in English?
You could call it like
Inertia. By inertia, it continues to go around like this. And it takes it 76 loops to come back again. Okay? It does 76 loops and comes back again here. So this is what it is. And the Tychosium tells you things, as I told you in the beginning of this show. The Tychosium, at the end, since it's so incredibly accurate, it can tell you other things. I discovered this long after, that Halley's comet moves from here to here in 44 days. Well, in one of my chapters of a book, I calculated the sun does this distance in 44 days. So the Halley's comet is doing the same speed, absolute speed in space, as the sun. So obviously it's a particle, it's a part of the sun that's been released and sometimes comes back to us and comes closest to Earth. Ask yourself this question. Why does Halley come closer to Earth than the sun? Isn't the sun a big attractor? Isn't the sun? No, it comes only at 0.4 AU to the sun every time it comes, but it comes at 0.1 to Earth. It comes closer to Earth than the sun. Halley's comet all the time. That's established. So why would this comet come closer to Earth than the sun? Maybe we will find out that the Earth is much heavier than the sun or something. Maybe Earth is a really, really heavy thing. Just like Tycho Brahe was saying. He was saying Earth is very sluggish. Why would it move so fast? Tycho Brahe also thought the Earth was very heavy. So we don't know how much those objects weigh. We have not put them on the bottom scale. We have not weighed the sun. We've only assumed that it's very, very heavy, but it's all made of the lightest gases we know of. Okay, so that's my last thing about Thales, because I really, if anyone is going to read at least one chapter of the book, it would be, I would recommend chapter 30, because you don't need to get into the details of, if you're lazy, let's say if you're lazy, you only have some time on your hands, just read chapter 30. Because if you read this chapter and after reading this chapter, you decide that it's all a long, long series of coincidences, there's nothing I can do to help you. Really, I can't help you. There's no way I can help you.
Right on, man. I mean, yeah, it's really compelling stuff.
We in our patron chat, I think, spent at least.
We've spent many different Sundays talking about the Tychosium model.
And everybody's just
Really?
fascinated by it because it's such a.
Oh, I didn't know that. Thanks for telling me. I'm sitting here a bit, feeling a bit alone, because in Italy there is very little interest. Of course, they don't read English.
If you wanted to come to one of our Sunday chats, I think people would just be totally floored if you wanted to come by and talk to people who are interested in it.
Love to. I'm always available and happy to talk about the Tychos, of course.
That's awesome.
So do invite me if you can. And I promise not to be. I promise not to be. To be so excited as I was tonight, because I've been partying with my 3 Swedish friends. We had some wine, so I wasn't quite as articulate maybe as I'm usually. But thanks for inviting me. Anyway,
yeah,
and thanks for your attention. So you're friends with Zarin Leff, or how did you get in touch with Zarin Leff, who has been presenting the Tychos in various conferences?
Yeah, he presented it at our conference, actually. Zarin's one of our patrons for a long time now. And he's just a really cool guy. We got to hang out in Austin together recently.
Okay.
And so, big shout out to Zarin, and thanks for connecting us with this.
Yeah, shout out to Zarin. He's been doing a great job, I think.
But yeah, thank you for giving us so much of your time and walking us through all of this and tolerating our pestering about the gravity situation. And honestly, I really think that it's not an unsolvable problem. And so Yeah, man. Best of
No.
luck, and
Yeah.
we'll be in touch. It would be really cool if you could come by our Patreon hangout and talk to our friends. It'd be really cool.
Okay. Cool.
But yeah, get back to partying with your buddies. That's what life's all about.
Yeah, they're Swedes on vacation. They're uncontainable.
That sounds
They
really
like to
fun.
party, and now they want to put some music on, I think.
Nice. Yeah, we didn't even talk about your music, but got some wild history there too. It sounds like.
Oh yes, I've been doing music for many years. It's my lifeline,
Me
music
too.
to relax and detach from the realities of the world.
That's what I'm
So,
planning on doing after we get off here.
cool.
I can relate.
Yeah.
But let's let you go, Simon. It's been a wonderful talking to you, man. I hope this isn't the
Yes.
last time we talk.
Yes, thank you so much for your kind questioning, and as Anastasia said, no, I'm not offended by you questioning the Tigers. It's exactly what I need or I wish for.
I appreciate
I'm not
that.
here, hoping for yes men to come and say, yeah, Simon, yeah, good. I mean, doesn't help me at all. I really
Anastasia
want-
and I could make a really mean AI if we wanted to. It would just give you hell about all your ideas.
yeah, give me hell. Give me hell. I'm absolutely
The worst, least popular chatbot
that's
online.
what I crave for. I crave for a bit of debate. I'm not shy or of discussing it, and I'm not saying that everything the Tigers must be true. Of course, I'm not that crazy. I just propose that it needs to be discussed. It needs to be discussed among open-minded people. That's all.
Agreed.
Cool. Yeah, we'll be putting it in front of people.
For sure.
All right, Simon. Thank you so much, sir.
It was
Yeah.
wonderful. Thank you.
Thanks.
Yeah,
Take
great
care.
work.
Yeah.
Take care, sir.
Have a good night.
Good night.
Bye, everybody.